A very good morning to everyone. Wishing you all a wonderful day ahead. With great honor, I, Ananya Pritilagna Biswal, a research scholar at the National Institute of Technology, Rourkela, and I welcome you all to the 5-day GIAN course on mini hydro power plant design and integration with DC microgrid. That is MSPD IMG 2024 from 18th to 22nd of November 2024. Under the aegis of Global Initiatives of Academic Networks, that is GIAN, an initiative by the Ministry of Education, Government of India, organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela. So, Lord Ganesha is an embodiment of wisdom, knowledge and learning. Let's seek the blessings in all spheres of life. So, please welcome the student group who is going to perform Ganesha Bandana. And simultaneously, we are going to start the day with this auspicious ritual of lighting the lamp of enlightenment. I would like to extend a warm welcome to the dignitaries to do the honors as we officially commence the day. Sir, please.
गणनायकाय गणदैवताय गणाध्यक्षाय धीमहि गुणशरीराय गुणमण्डिताय गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय बालचन्द्राय श्रीगणेशाय धीमहि.
Thank you everyone. Thank you students. We are really fortunate to have such eminent guests amongst us. Now I request all the distinguished guests, the Honorable Director of NIT Rourkela, Professor K. Umamaheshwar Rao, esteemed Foreign Faculty Professor Anura Wijayapala, the Dean SA Professor S.K. Pratihar, the Head of the Department Electrical Engineering Professor K.B. Mohanty, and the GIAN Local Coordinator Professor Sisir Kumar Sahu, the GIAN Course Coordinators Professor Monalisa Pattnaik and Professor Indrajit Sarkar sir to join us on the stage. Please sir. Now I request the GIAN Course Coordinator, Professor Monalisa Pattnaik, to provide a brief introduction regarding this course. Ma'am, please.
Good morning, all. Honorable Director, NIT Rourkela, Professor K. Umamaheshwar Rao, esteemed foreign expert, Professor Anura Wijayapala of University of Moratuwa, Sri Lanka, Dean Shrik, Professor S.K. Pratihar, GIAN Local Coordinator, Professor S.K. Sahu, HOD Electrical Engineering, Professor K.B. Mohanty, the other GIAN Coordinator, Professor Indrajit Sarkar, my dear colleagues, participants from various institutes attending this event both in offline and online platforms. A warm welcome to all of you to the inaugural ceremony of the first GIAN course of Phase 4 at NIT Rourkela on mini hydropower plant design and integration with DC Microgrid, MHPD IMG 2024. This GIAN course is meticulously designed in coherence with Global Energy Strategy ES 2050 goals to impart knowledge about the developments of mini hydropower plant design and the DC microgrid, starting from the fundamentals to the practical demonstrations with clear objectives. As a GIAN course coordinator, I took the opportunity to invite Professor Wijayapala of University of Moratuwa, Sri Lanka to NIT Rourkela and hosted him to deliver lectures on mini hydropower plant design and other details. This course will further explore the topics such as power converters for these mini hydropower plants, concept of microgrids, power management, and energy storage solutions, along with real-world case studies highlighting successful deployment of these mini hydropower plants, the challenges and the opportunities. In this course, we have 55 participants registered in both offline and online mode. This course will also provide many opportunities for the participants to interact with the foreign expert throughout. I encourage each one of you to actively participate in the various sessions, to ask questions, and to engage yourself in fruitful discussions. By the end of this course, and I am quite certain that you will have a profound understanding of mini hydropower plant design and integration with microgrid. More importantly, you will be equipped with the tools and insights to make a meaningful impact in the field for contributing to the development and implementation of clean energy solutions. Now, I would like to express my sincere gratitude to our esteemed expert, Professor Anura Wijayapala, whose proficiency and dedication has encouraged us to organize this course. His commitment is truly commendable, and we are fortunate as he is guiding us on this transformative journey. I am very thankful to Ministry of Education for sponsoring this GIAN course. I extend my sincere thanks to National GIAN Coordinator Professor Anil Agrawal of IIT Hyderabad. My sincere thanks to the Director of our institute, Professor K. Umamaheshwar Rao, for his constant inspiration to conduct such type of programs at our institute and for gracing this inaugural event apart from his busy schedule. My heartfelt gratitude to Professor S.K. Pratihar and Professor S.K. Sahu for supporting us to conduct this GIAN course. I am also grateful to our HOD, Professor K.B. Mohanty, for extending his wholehearted support to organize this program smoothly. I must thank the other coordinator, Professor Indrajit Sarkar, for his constant support in conducting this event. I am also thankful to all the faculty and staff members of this institute and our department for attending this event and encouraging us. Finally, I would like to thank all the students of our department and the volunteers and the other participants from the various institutes. Once again, I welcome you all to the GIAN course MHPD IMG 2024. Let us make the most of this opportunity and plan a path for green and sustainable future. Thank you all. Thank you.
Thank you so much, ma'am, for such valuable information. Now I request the GIAN local coordinator, Professor Sisir Kumar Sahu, to welcome the audience by throwing some light on this GIAN initiative.
Good morning to all. Respected Director, NIT Rourkela, Professor K. Umamaheshwar Rao, the Foreign Expert of the GIAN course, Professor Anura Wijayapala, Head of the Department of Electrical Engineering, Professor K.V. Mohanty, Course Coordinators, Monalisa, Pattnaik and Professor Indrajit, Sarkar. Dear faculty colleagues, participants, students, ladies and gentlemen. As the Institute Coordinator of the GIAN program, I will talk regarding the GIAN program only. So the GIAN is a program of the Ministry of Education, as everybody knows, is designed to tap the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the institutes of higher education in India, to augment the country's existing academic resources, accelerate the pace of quality reform, and elevate India's scientific and technological capacity to global excellence. GIAN enables institutes of higher education in India to invite and host internationally renowned academicians and researchers, facilitating the co-teaching of advanced courses to Indian students and fostering collaborative relationship with experts from around the world. The program offers great opportunities for Indian students and professionals to closely interact with international experts for a considerable duration. By participating in GIAN, students gain invaluable insights, practical knowledge, and international perspectives that enrich their academic pursuits and future careers. Furthermore, GIAN offers international experts a unique opportunity to familiarize themselves with India's academic environment. By interacting with local students and faculty, these experts can explore potential collaborations, share their expertise, and contribute to the advancement of knowledge across diverse fields. The scheme was launched in 2015 and 3 phases have already completed successfully under the supervision of IIT Kharagpur as the central nodal agency. For the conduct of the 4th phase, IIT Hyderabad is appointed as the central nodal agency for administration of the course. NIT Rourkela has till now conducted 24 courses. In the current phase of GIAN 4, that 11 courses are already approved, and this is the first course we are planning to do it. I wish all best wishes for the persons involved in making the course a success. Thank you very much.
Thank you so much, sir, for providing us this great opportunity. Now I would like to request our Honorable Director, Professor K. Umamaheshwar Rao, to give a floral welcome and present a memento to the esteemed foreign faculty, Professor Anura Wijayapala. Thank you very much, sir. Now I would like to request the Head of the Department Electrical Engineering, Professor K.B. Mohanty, to felicitate our Honorable Director, NIT Rourkela, Professor K. Umamaheshwar Rao, with a bouquet and a memento as a token of appreciation. Thank you very much, sir, for doing this honor. Again, I request the HOD Electrical Engineering, Professor K.B. Mohanty, to acknowledge the Dean SR, Professor S.K. Pratihar, as a token of love and honor. Thank you very much, sir. Once again, I request the HOD Electrical Engineering, Professor K.B. Mohanty, to express our gratitude to the GIAN Local Coordinator, Professor S.K. Sahu. Thank you very much, sir. With great pleasure, I would like to request GIAN course coordinator Professor Monalisa Pattnaik to greet the HOD Electrical Engineering Professor KB Mohanty by offering the memento and bouquet. Thank you very much, ma'am. Now I request the HOD Electrical Engineering Professor KB Mohanty to deliver an inaugural speech and provide some information about the department. Please, sir.
Respected Director Professor K. Uma Maheshwar Rao, GIAN Local Coordinator Professor S.K. Sahu, Dean Srik, Professor S.K. Pratihar, and foreign delegate Anura Wijayapala, and coordinators Professor M. Pattnaik and Dr. Indrajit Sarkar, and all the participants of the GIAN course Mini Hydro Power Plant Design and Integration with DC Microgrid, and other faculty members who are present, and all the coordinators and all the volunteers. Very hearty welcome to the Department of Electrical Engineering conducting the first GIAN course of the 4th phase, and this is quite great achievement for the great step of the department and the coordinators to organize the first GIAN course of the 4th phase. And our department has very good tradition of conducting courses. Our department is very old, started in the year 1961, and since then many students have graduated and obtained higher degrees like MTech and PhD degrees, and our students are working all over the country and globally, and also in occupying many important positions in academic institutions, even including director of IITs. So that is a great achievement for our department. And our academics wise, our department has done a great, and our students, so it has earned laurel for the academics and research, and I hope all the participants will benefit from this GIAN course, and I wish a great success to this GIAN course. Thanks all.
Thank you very much, sir, for delivering the welcome speech and sharing your valuable insights and experiences. We now invite Dean Esa and Professor S.K. Pratihar to address the session with a welcome note. Please, sir.
Good morning, respected guests on the dais, Professor K. Uma Maheshwar Rao, Director of our institute, esteemed international expert, Professor Anura Wijayapala, Professor Shishir Kumar Shah, GIAN coordinator of our institute, Professor K.B. Mohanty, HOD Electrical Engineering, NIT Rourkela, Professor Monalisa Pattnaik, and Indrajit Sarkar, course coordinator of today's, distinguished faculty members, esteemed colleagues, distinguished guests, dear students, ladies and gentlemen. It's a great pleasure and honor for me to stand before you today to inaugurate our initiative on mini hydro power plant design and integration with DC Microgrid. This program is under the Global Initiative of Academic Networks, a flagship program under Ministry of Education. This initiative represents a significant step in our commitment to fostering collaboration, enhancing learning, promoting international knowledge exchange across the borders. GIAN's vision recognizes the power of collective knowledge and importance of shared experiences in education. In an era where challenges are increasingly global, the need of interdisciplinary approaches and cross-cultural discussions has never been more critical. Through GIAN, we aim to break down the silos that often exist within academic disciplines and encourage a holistic understanding of the issues we face today. GIAN provides a platform of international knowledge exchange. In today's interconnected world, the flow of information across the border is vital. By participating in this course, you will be engaged with experts and practitioners from various countries, gaining insights that exceeds geographical boundaries. Today's program on designing and integrating mini hydropower plant with DC microgrid represents a significant step in our mission for sustainable energy solution. It's a testament to our commitment to fostering innovation and collaboration in the field of renewable energy. As we gather here, we are reminded of the urgent need for clean and sustainable energy resources. Climate change, environmental degradation issues, together with the ever-increasing demand for clean and green energy, have placed immense pressure on our existing power system. In this context, harvesting power from renewable sources has never been more crucial. Mini hydropower plant, in particular, offer a promising solution by providing a reliable, environmentally friendly energy source, especially in rural areas and remote areas where electricity is limited. Today, we embark our journey to explore the design and integration of mini hydropower plant with DC microgrids. This event approaches not only enhances the efficiency and reliability of energy distribution, but also align perfectly with the global movement towards decentralized energy system. By integrating mini hydropower plant with DC microgrids, we can create robust energy network that empower communities, reduce transmission losses, and optimize energy utilization. The significance of this initiative lies not only in its technical aspects, but also its potential to drive social and economical development. Reliable access of energy is the cornerstone for progress, enabling education, healthcare, and economic opportunities. By equipping our students and professionals with the knowledge and skill to design and implement this system, we are investing in a sustainable system for generations to come. I urge all participants to take full advantage of this program, engage deeply with the curriculum, collaborate with your peers, draw upon the wealth of knowledge that our esteemed faculty brings to this initiative. This is a unique opportunity to learn not just about the technical intricacies of mini hydropower plant and microgrid integration, but also broader implication for society and environment. As we move forward, let us foster a spirit of collaboration and innovation. The challenges we face in the energy sector are complex and multifaceted, requiring interdisciplinary approaches and diverse perspectives. By working together, we can leverage our collective expertise to develop solutions that are not only technically sound, but are socially responsible and environmentally sustainable. In conclusion, I would like to express my gratitude to everyone involved in making this initiative a reality. Your dedication in advancing knowledge in renewable energy and commitment to sustainable development is truly commendable. Together, as we embrace this opportunity to lead the way in designing and integrating hydropower plant with DC microgrids, contributing to a sustainable energy future that benefits us all. Thank you. I wish you all a fruitful and inspiring journey throughout this program.
Thank you so much, sir, for your encouragement. I am glad to invite Director NIT Rourkela, Professor K. Umamaheshwar Rao, sir, to address this event with a delightful note, please. Sir.
The most distinguished dignitaries on dais, and then we have the foreign expert as the chief guest, Professor Anura Wijayapala from Moratuwa University, Colombo, and Professor S.K. Pratihar, Dean Shrik, Professor Sisir Kumar Sahu, GIAN local coordinator, Professor K.B. Mahanti, and Professor Monalisa Pattnaik and Professor Indrajit Sarkar on the dais, and other my faculty colleagues of the dais and the participants across the country on this 5-day GIAN program on the mini hydro power plant design and integration with the DC microgrid. And I take this opportunity to welcome you all to NIT Rourkela, and we have just set in the winter, and at this note I would like to really mention that the need for the power plants, whether they are mini or mega power plants, alternative power source in our country is far more essential, or rather globally it is the need to reduce the carbon footprint. I think the impact of carbon footprints, I really do not know how many of us have realized, but then I request and I appeal to everyone, right, that it is time for us to really realize that the impact has already been very harsh, so much so that, and there is a warning that the temperature is likely to increase by 1 or 2 degrees centigrade in very, very soon, in years to come. And then we may not really feel that what really happens if it is 1 degree increase, right? It doesn't really change much. But then what really happens is that our dependence on power is increasing, okay? And only now, today, I am not seeing that AC is not running. Otherwise, what is happening is that perpetually we are trying to find comfort within the 4 walls, switching on the ACs, but then we are not really concerned about what is happening on the other side of the AC unit. Okay, how much exactly the heat or the hot air it is throwing out to the environment. Again, you go back from this PP auditorium and then you go back into the same environment where you have thrown out this particular hottest air. Okay, and then now the sitting in the directorate or the office of the director, I really find every day there is a need for large number of AC units. Okay, me per se, I do not sit in an AC room. I keep my windows open. I think most of my faculty know that one. They are a little scared to get into my room. The reason is that my room is hot physically, hot for the aspects which they really come with the ideas, and then try to, both ways it is, symbolically it is a hot room, hot chamber. It's not that I am single as a lone fighter that I am trying to discourage the AC, but then the question is that what is the extent of sustainability? Professor Pratihar was using that word sustainability. What temperatures can we sustain? What exactly is the youngsters? I am just trying to really tell you that. I am from Telangana, right, in Hyderabad. Actually, my native place is not Hyderabad. I am close to Hyderabad, where during our time also the summer used to be very harsh. But then I remember that we never had even a fan. We never had a fan. In my 8th class, we had the power in my house. But then it was sustainable. My question here is that the question of, quote unquote, the word sustainability, why it is not becoming sustainable in the present context, the same conditions which we were really living in is not sustainable. Right? People really want, NIT Rourkela, people really want, my students, my faculty, my staff, my everyone, right? They want to live in 16 degrees centigrade. Right? So when you want to really live in 16 degrees centigrade, how much of the demand of power that you are really creating? Why hasn't it become sustainable for us to live just with a plain simple fan? Why hasn't it become sustainable? This is one question which we have got to ask. Second question which I am just, the youngsters, because tomorrow belongs to you. We are not going to be present to witness the tomorrow which is going to be absolutely horrible. Horrible in the sense where you have no control on the climate which is really changing drastically. If you have noticed, Rourkela, at one time I was told that it is Rourkela, means it's that rains are really very frequent, and then I don't say it's a torrential rains, but then it rains persistently to 1200 to 1400 millimeters annual rainfall. Okay. When we are now, what exactly is that connection to hydropowers, whether it is mini or mega, and Professor Anura Wijayapala will appreciate that one. Sri Lanka is one place where, right, Jaffna, and there are so many other places in Sri Lanka where you have the waterfalls, and then Sri Lanka, even yesterday it was raining. Yesterday there was a thunderstorm in Sri Lanka, Colombo. Okay. It is unseasonal. And I was, 2 days back, I was in Goa, and it rained heavily. Heavily means I was little in a doubt whether I will be able to reach airport, Mopa airport, which is 85 kilometers from the NIT Goa. Okay. That was the extent of rain. Okay. What I am saying is that this unseasonal, unpredictable behavior of the nature, in its manifestation in various forms, it is going to really have a terrible impact on the youngsters who are here. I am just trying to remind you that mini power plant is possible provided you have water. You have rivers which are existing. Okay. I am from Hyderabad, means just after my schooling in a different place, when I shifted to Hyderabad, during our time in Hyderabad, it used to have more than 3,000 lakes and water bodies in and around Hyderabad. Today, right, all of them have vanished. Only superstructures have come up, 35, 40 and close to even 50-story buildings are coming up. Civil engineering, Sisir Kumar Sahu is growing, but then structurally he is growing. The issue which we are forgetting, all of us are forgetting, is that unless you have the ambience needed to generate hydropower, right? This GIAN is a Sanskrit word, though it has the global initiative of academic networks, right? The other meaning of this one, acronym, GIAN, is wisdom, right? GIAN is wisdom. The wisdom call here is that we should all try to realize that whether we are in a position to plan for tomorrow the mini power plants, hydropower plants. Let us think about that one first. Afterwards, putting it in the grids or a networking. Once we really have that potential to generate power through mini hydro plants, then we can think of putting that in the grid. Okay. It's like first you clear your JE or clear your GATE examination. Then think of which NIT or which IIT that you have got to take admission in. So we are exactly now at this particular juncture, like, can we clear this examination of making our lives sustainable? This sustainability is tougher than JE and then GATE. Because JE and GATE is there where you can sit in a closed room which is AC giving you 16 degrees centigrade. You can still go through the books and then rut through the fundamentals, and then ultimately it is MCQ, multiple choice questions, right? One is correct answer, 3 are wrong, or one is the most probable answer, second is possible, and then the other is a positive, and then other is a wrong answer. There some bit of gambling can really help you. That probability will help you to identify at least 30% of the answers even without knowing anything. No GIAN. In spite of that ajnan, right, we can still crack 30% of your question paper. But then this is not going to really do that one. This is not going to give you that particular choice or freedom. Right? I am taking this particular platform on the morning of today, the first day of the week, right? I am appealing to the youngsters across the country. Please try to make this planet livable, sustainable for not only for our generation, for the next generations to come. Okay? For that, you have got to take care of air, you have got to take care of water. Right? Today, our wisdom is that we are taking water from these bottles. Right? This is whatever the type of water it is carrying. It looks transparent. There is no turbidity as far as Shishir Kumar Sahu is concerned. The water bottles is containing water purchased at some cost. It is not turbid. Will there be water for you to place it in the bottles? Today, the papers say that 40% is the deficit in the rainfall in Western Odisha. Last year, it was 40% deficit in rainfall. Prior to that one, 22 when I came, it was around 30 to 40%. Means consecutively, every year after year after year, right, there is a deficit in rainfall of substantial percentage. पानी कहाँ से मिलेगा? ये mini hydro plant के लिए. Where do you get this water from? We are all focusing on Mahanadi. But how long it will sustain if we try to really, we are abusing the soil by rampant usage of plastic. I am emphasizing that rampant. Plastics, right? You have no idea. You just try to see any city. You go around the country. You just see the dustbins around. अगर वो अंदाज़ा नहीं है, Sector 1 जाइए. Sector 1 all the stationery shops, medical shops, वहाँ पर खड़ा होकर के देखिए 5 मिनट. How much of the plastic we are throwing on the streets and then the garbage bin? Where is this plastic going? It is making the soil impervious. बारिश जब गिरेगा, पानी सूखना तो चाहिए ना, मैडम लोग. If it is not percolating, soaking into the soil, it is not percolating and recharging the ground water table. If it is not recharging that one, right? Today, when your mobile gets drained off, you recharge that one. There should be some money within your purse, in pockets, to really buy the required recharging of your mobile. But then if you do not have that capacity to recharge our groundwater table, where do we go for water? Where do we go? महानदी भी ज़्यादा दिन नहीं चलेगा, वो भी सूख जाएगा. जैसे जैसे हम यह कह रहे हैं ना, the amount of water draining into the ocean, we are not taking account of that one. We are absolutely not taking account of that one. I'm not looking at the power plant. I'm only looking at the resource to the power plant. Right? And then we are living in a desert, and then we are making a plan for shadow. Where is the shadow coming from in a desert? We are planning for power plant, hydropower plants, sitting in a time when the last 3 consecutive years there is a 40% deficit in rainfall. Where is the source of water? Koel River, from where we are drawing water into the campus, please go and then see that one. I must have told this particular statement. This must have been 100th time in these 3 years. I must have requested my students, go and then see the Nala. Whether there is water in that for us to draw for our campus. Is our life on campus sustainable? I just want everyone to understand the word sustainability. Sustainability is, in plain and simple terms, जितना हमें चाहिए उतना ही लेंगे. लेकिन आज का दिन में, I'm sorry if I have switched to Professor Aruna, right? I just switched on to Hindi. Forgive me for that one, right? So now the question here is that today we are in a mindset, a thought process that since the independence, I am addressing 4 of you and then for some of you here, okay, not the older ones who are already into middle 55s and all. We are already in a mindset that everything in this country is free because we are independent India. Free. फ्री में मिलता है, यहाँ तक कि खाना भी फ्री में मिलना चाहिए. एटलीस्ट इट शुड नॉट बी मोर देन 120 रुपीज पर डे. पिज्ज़ा फ्री में मिलता है मैडम. पिज्ज़ा कितना दाम है? 300 or 400 rupees. Zomato is not free. Right? None of these foods which you are consuming on a daily basis is not free, but then we are presuming that this electricity which we are using in these rooms is free. Water that we are using on campus is free. The facilities that are provided to you in your hostel rooms, like your washing machines, you think that it is so much free that I can even blast them with the bombs, Diwali bombs. Right? Yes or no? Have you ever questioned in your life, have we got freedom to abuse our own property? I have got so many pictures of this recent Diwali, the catastrophe that it has created on my campus. If this is the youth who have cleared JE and then GATE, carry with their minds that हम विध्वंस करके ही छोड़ेंगे, ये ज्ञान है या अज्ञान है? And then in the same tone, right, we are also becoming absolutely ajnan about what exactly is our responsibility as the citizens to make this society, to the planet. If forget about your planet, just make your own campus sustainable. It's a serious concern, my dear faculty, friends, and then students across the country. I'm forcibly inviting winter. Otherwise, I could have been as comfortable as our guest from Sri Lanka, Anura Wijayapala, without any bandi this one. I just wanted, because November has come, 3rd week of November has come, I am not taking out my sweater out. At least to make myself comfortable in my mind that I want to wear some winter garments. There is no winter. Look at Pratihar. He's still in summer. If this summer continues, my dear, if this summer continues throughout 12 months, it won't be a sustainable place. Forget about mini or mega hydro plant. There will only be tears, will not be any water. You cannot generate power from tears. आंखों के आंसू ही बच जाएगा, वहाँ से पावर तो जनरेट नहीं होगा. नैनो पावर प्लांट भी हो, आंखों क्या आंसुओं से पावर तो जनरेट होगा नहीं. The truth again is that India is a country where more than 50, close to 60% of the power is generated by burning fossil fuel. Have you ever thought what could be the alternative to this country? There is a warning, COP countries, COP में, that you have got to, unless you cut down the carbon footprints, the life on earth is going to be very soon, I don't say extinguish, but then it is going to that human race ending. It is the beginning of COVID only. It is not the end of COVID. COVID के इसके पर्यांत बहुत सारे चीज आने वाले हैं. Right? So now, all your knowledge which you are gaining should really look for alternative sources of power so that we can reduce this carbon footprints. I think I spoke little more than what is required, but then it is helpless condition with which I am speaking, that we are having very attractive titles in GIAN program, very, very attractive titles, and then need is there. But then whose need is this? Organizers? Is it Professor Monalisa's Pattnaik's requirement, or Professor Sisir Kumar Sahu's? It is your requirement. If you don't think that it is your need that they are providing you, then there is no answer to the problem which we are heading towards. We are heading towards unsustainable planet. Thank you very much. I'm sorry. Firstly, I should have said that one. I'm sorry for keeping you waiting for 5 to 7 minutes. I was told by my office that there is a GIAN program, Wisdom Call, right, at 9:45. Right, so no, I was just getting to my breakfast, and so I got late. I'm very extremely sorry for the information which I got late. Thank you very much. And then I wish the youngsters, please, it's an appeal. Become responsible here. Please become responsible. Let us take care of the campus first, our city next, and our country day after. Thank you very much.
Thank you very much, sir, for adding such immense value to our gathering. Now I humbly request the foreign faculty, Professor Anura Wijayapala, to grace this event with few words.
Good morning. Professor Uma Maheshwar, Director of NIT Rourkela, Professor S.K. Pratiha, Dean SR, Professor K.B. Mohanty, HOD Electrical Engineering, and local GIAN coordinator, Professor Shashi Kumar Sahu, and this course coordinators, Professor Monalisa and Professor Indrajit, and the faculty members who are present here, and the participants who are joining physically and online as well. Ladies and gentlemen, good morning once again to you. Thank you very much for coming here today, this morning, spending your time for the inaugural session here. And the course will expand for 5 days, mostly on mini hydro and then how to grid connect it to DC as well as, if necessary, into AC as well. And I think Professor Uma Maheshwar highlighted the need for shifting to clean energy as soon as possible. The world is already not only late, it is too late. And the envisaged temperature increase, which is about 1 degree Celsius from pre-industrial to the present, I don't think that with the present measures can be held between at least limited to 2.5 degrees by the end of this century, and that is very unlikely. So we can see the number of environmental calamities in India. For example, heat waves were not heard 15-20 years back, and now every year heat waves are visiting India, putting many people in trouble, especially the poor, and many parts of the other parts of the world as well, in Europe and so on. And therefore, renewable sources are the only option for creating and generating energy. And when we talk about large number of types of renewable sources, at the moment, especially in South Asian perspective, the three most commercially viable are solar, energy and hydro, because other ones are not that environmentally viable. Biomass is there. Biomass is carbon neutral. Therefore, it is not significantly contributing to carbon neutrality, only to some extent. But solar, wind and hydro are the most conducive. But out of these three, solar and wind has a major issue because they are intermittent. Their solar energy can be varying in 5 minutes from 100 megawatt to 20 megawatt. Then there should be some other power plant in the backyard or batteries in the backyard to take up the deficit. Similarly, wind is not that intermittent, but wind is also intermittent. But whereas hydro or mini hydro river flows are not changing that fast. Maybe for a day it will be almost constant. So for the system control operator, hydropower plants are not a threat about intermittency challenges. Therefore, mini hydros are important. And in Indian context, from my research in the available data, the Ministry of Power has identified over 20,000 megawatts of power plants, and only 25% of that have been developed. So there are 75% more identified mini hydro sites in the country which have to be developed and which are very viable energy sources and local too. And therefore, there is a big industry gap immediately that have come up, and with the pressure for shifting toward renewable energy, it is mandatory that the necessary knowledge be imparted to the young generation, especially I see a lot of young faces here, and therefore they can contribute in numerous ways in the industry for the development of these small hydropower. We call them micro hydro, mini hydro or small hydro, different names, but they mean the same. And before concluding, I would like to show that there's a big contrast between the large hydro and mini hydro. Mini hydro power plants are almost always run-off river power plants. You take water from a river, use it in a power plant, immediately put back the water in the river. Therefore, downstream impact is very limited. But in your develop a large hydropower plants, there is always a reservoir which will stop the water which has been flowing for thousands of years, and you put them in a reservoir and collect water and then use it as at your will. So which will have drastic impacts on the downstream ecological systems and on the people who have been using. Therefore, mini hydros or run-off river power plants are very much environmental friendly and does not pose any threat to the downstream people. Therefore, are more welcome in the present day world. With that, I would like to conclude. We are a little bit short of time. Therefore, I once again thank all the dignitaries in here and also the other faculty members who are present here, gracing the occasion, and to the participants for joining this course. Thank you very much. I look forward to discuss with you these topics during the next 5 days. Thank you.
Thank you so much, sir, for your inspiring words. They have truly enriched us. Now I would like to propose a vote of thanks to all the dignitaries and participants. As we come to the end of the inaugural session, on behalf of everyone here, we would once again like to thank our honored guests for their invaluable contributions and for gracing us with their esteemed presence today. I would like to thank our Honorable Professor K. Umamaheshwar Rao, sir. We really appreciate your presence here today, sir, despite your busy schedule, and for contributing greatly to this event. And as sir also highlighted the impact of sustainability in our daily lives, I also request everyone, my colleagues, faculties, professors, to take a stand and initiate with its our own selves, like from starting from our home, then our campus, and then to our country and globally. Thank you so much, sir, for your impactful insights. Thank you. Now we are moving forward. We are also very grateful to our esteemed foreign faculty, Professor Anura Wijayapala sir, for being here today. In future also we hope for many such collaborations, sir. Thank you so much, sir. And sir has also highlighted the word intermittency. That's we are here to integrate our in renewable sources to our DC microgrid because of the intermittency nature of like solar, wind. So thank you so much, sir, for your experiences, sharing your experiences with us. Now I would like to extend my heartfelt gratitude to our Dean, sir, Professor Pratihar sir. Thank you, sir. Your presence on this special occasion really matters a lot. Now I would like to express my sincere gratitude to the head of the department, Professor K.B. Mohanty sir, for your kind support throughout this course. Thank you so much, sir. The GIAN local coordinators, Professor Sisir Kumar Sahu, who has also emphasized the use of renewables and this mini hydropower plant impacts on our DC microgrid. Thank you, sir. And thank you for your cooperation and choosing NIT Rourkela. Moreover, the GIAN course coordinators, Professor Monalisa Pattnaik and Professor Indrajit Sarkar sir, thank you for encouraging research scholars, students towards the renewable energy growth and development. As the name suggests, hydropower plant design and integration with DC microgrid. Ultimately, such curriculums not only help our country to achieve net zero emissions by 2070, but also to reach the target of generating 500 gigawatt of renewable energy production. And last but not least, thank you so much the volunteers for your commendable efforts to ensure the smooth conduction of this course. As we close the day, let us heartily applaud the chairs for setting the stage and eloquently outlining the purpose of our gathering. Thank you everyone for joining us and showing appreciation and gratitude. For a short refreshment, I would like to invite you all to join us for high tea. Thank you everyone. Have a good day. Renewable Energy Company in Sri Lanka from February 2018 to February 2020. He is a board member of the Smart Energy Council, Sri Lanka. Currently, he is serving as a professor and the head of the Department of Electrical Engineering, University of Moratuwa, Sri Lanka. So now I request Professor Wijayapala to proceed and start the session. Thank you.
Good morning. I hope I am audible to all of you, the participants. Can the remote participants confirm they can hear me to the controller? Okay, right. Okay, good. So, so in the first session, in the lecture 1 and 2, we will be taking up introduction to mini hydropower and use of contour maps, because the contour maps play a pivotal role in designing and implementing mini hydropower plants, small hydropower plants anywhere in the world. So, so here I have put a picture from an Indian small hydropower plant just to begin with, so that you get those who have, maybe some of you have visited small hydropower plants and large hydropower plants as well. We will see why the difference between the large hydros and mini hydros, and the importance of mini hydros compared to large hydros. Here we can see, I am sure that electrical engineers and other engineers are familiar with the typical components, which we are going to see in detail later. We can see in this power plant the penstock, and the penstock is supported by and held by anchors, etc., concrete anchors we can see, and the power plant we can also see. And then the tail race water, that is after water goes through the turbine, goes back to the river, we can see. And the electrical components, little bit we can see from this picture. The overhead transmission line we can see here, and also the grid we can see, where the voltage is stepped up from the generating voltage to the transmission voltages. So, we will go through part by part of many of these components from a hydropower plant developer's view, because a hydropower plant is a multidisciplinary project, and there is a technical issue. So, let us see. In the first session, they are sorting out various technical issues. Let us see. Okay. So, I was just speaking on a hydropower engineer's role, because a hydropower plant comprises of many kinds of engineering solutions. For example, a lot of civil engineering is involved, and a lot of mechanical engineering is involved. For example, penstock is a mechanical engineering involvement, and the turbine is a mechanical engineering main item, and there are many. And then the electrical engineers have to play a pivotal role there, because it is electricity generation. There is electricity generators, and then the control equipment, control systems, and then the SCADAs, and then various other devices controlling the electricity flowing from the generators to the network. And then there are the hydrologist involvement, because we are dealing with hydropower which is coming in a river. So, their estimations are required, where you have to judge how much electricity you can generate momentarily, as well as how much energy you can generate throughout a year, which you can sell as a commercial item to a electricity grid and earn returns for the investment. So, all these things are there. So, the hydropower engineer really has to coordinate all these things. So, in this course we are developing necessary skills for a hydropower engineer. So, therefore, we will neither try to become a civil engineer, no an electrical engineer, no mechanical engineer, but we will try to have a combined impact, combination of knowledge from a hydropower engineer, how a hydropower power plant should be planned and implemented. And for each subsection, he will use, for example, to design and construct the powerhouse, he will assign the necessary sizes to a civil engineer, who will design the powerhouse depending upon the local conditions, soil conditions, etc. And similarly, he will design, hydropower engineer will design what should be the penstock diameter and the thicknesses at different levels, and then he will ask the mechanical engineer to do the final design as to how to weld the pipes between pieces and so on. So, he will use expert mechanical engineer for that, but the hydropower engineer will do the sizing of components and the lengths, etc., and the location of the various components. All these things the hydropower engineer will do. So, in this GIAN course, we are looking from a hydropower engineer's point as to how to plan and develop and implement a hydropower plant, especially a small hydropower plants. Okay. So, I have done my research to find out the hydropower situation, especially small hydropower situation in India, how it stands today. So, as per the Ministry of Power, number of identified locations of small hydropower, 7,000 plus sites they have identified, and they have estimated they can generate about 21,000 megawatts, sorry 21,000 megawatts, that is a pretty big, 21 gigawatts of electricity from these 7,000 plants. And by 2020, only 1,100 plants have been developed throughout the country. Therefore, there are plenty of other opportunities where small hydropower plants can be implemented in India, and the total capacity developed by 2020 is mere 4.7 gigawatt or 4,700 megawatts out of 21,000 megawatts. So, there are a large number of small hydropower potential sites available throughout the country which can be developed, and in my experience I know throughout the world that all these power plants are very much commercially viable. Therefore, there are no need for the government subsidies and also government funding. They can be developed by private sector investments. Therefore, funding requirements are not an issue. So, they are commercially viable, producing cheap electricity and sustainable electricity. And there is a confusion about this different names used in hydropower industry, small hydropower industry. I am sure you have heard about words like micro hydro, mini hydro, and sometimes for a smaller units pico hydro, and starting from recently the word small hydro. So, some classifications used in India, up to 5 kilowatt projects are sometimes classified as pico hydro, and up to 100 kilowatt from 5 kilowatt micro hydro, and 100 to about 2000 kilowatts mini hydro, and up to about 25,000 kilowatts small hydro. But there are no hard and fast rules about this. There are no standards, IEC standards or BS standards saying this is the classification. So, it is a country dependent classification. For example, in USA where they have very large hydropower plants, they call up to 100 megawatt small hydropower plants, and China 50 megawatt up to 50 megawatt they call small hydropower plants, and in Sri Lanka we call up to 10 megawatt or 10,000 kilowatt as small hydropower. So, this is the Indian classification, but of course, there are no hard and fast rules. So, I prefer to use small hydro for the entire cross section here. So, up to from 0 to say 25 megawatt in Indian context we can call small hydropower. So, we are discussing on this topic. So, I will be using small hydropower term small hydropower for the entire cross section of these projects less than 25 megawatt. In Sri Lanka we call up to 10 megawatt as small hydropower. And here is how the potential sites are spread across different states. We can see some states are very lucky, they have many opportunities. For example, Himachal Pradesh, the capacity estimated capacity is 3,400 megawatts, and out of that only about 1,000 megawatts are constructed and under construction. So, a lot of opportunities, and similarly other, and I have had some opportunities in doing some research and helping some friends in Kerala for the development of small hydros and identifying sites some time back, and I will show you a picture where we visited some sites. So, there also they have many opportunities. So, you can see there are large number of opportunities for the future. For example, if you take Sri Lanka, we have developed most of the mini hydro opportunities. So, there are no more commercially viable, practically implementable small hydropower opportunities in Sri Lanka. There are few, but the picking up is very slow because of the various other reasons, like you have to relocate families, etc., when you are doing it in townships, etc. But when you are doing them in very remote areas, those problems do not exist. But in Indian context, these things are in remote areas, I believe, and therefore, they can be easily implementable. And we can also notice here that these projects are not large. For example, if you take Rajasthan, right, there are 64 projects having a capacity of 51 megawatts, right. So, that shows that each project on average is about 1 megawatt or less, right. They are small projects, not very big projects, right. So, although we earlier told up to 25 megawatt small hydros, but most of them come into less than 10 megawatt range. If you take Kerala, for example, 238 projects, estimated capacity is 647, that is about 3 megawatt size the capacity each. There may be couple of projects having higher capacities, but on average less. Therefore, in small hydro developments, most of the projects fall into the category less than 5 megawatt capacity, implemented ones. There are occasionally larger power plants as well in South Asian context, but if you take China or USA, maybe the projects are much larger because their opportunities are much bigger. And here are some pictures taken during our visits in Kerala in 2004 with my 20 years younger those days, and see our team visited. He is Mr. Nair, an Indian gentleman, and we helped him to identify. He wanted to make some sites selected for his project. We helped him to do it because he was helping us in Sri Lanka in sourcing machines from India. We purchased some machines through him from a company in Delhi, and so we had some relationship. So, when he wanted to develop some projects in Kerala, we visited together with him and helped him to identify some commercially viable options for development. And so it is important to know the comparative costs. If you take renewable energy, solar, wind, renewable mini hydro stand as very commercially viable projects to be implemented. So, it is as engineers we should know roughly where the costs stand, in what range we are talking about. We know if you take a large hydropower plant, we normally say cost in US dollars per megawatt, that is to develop 1 megawatt, how many US dollars. So, we can say in certain states like Himachal Pradesh and so on, the cost is somewhere about 1.4 $1 million per megawatt, that is to develop a 1 megawatt project, it will cost something like $1.4 million in these areas. But in some other states it might be even cheaper. It might be even cheaper because there maybe local costs are lower, labor costs are lower, and also maybe the opportunities are more easy to develop. So, they are less than 5 megawatt capacity, and when it comes to between 5 and 25 megawatt, economy of scale comes up. Therefore, costs goes down further, because larger power plants when you develop, naturally your costs go down in small hydro cases. But when it comes to large hydros, costs are much higher because there is a reservoir. Cost of the reservoir is huge. You have to have an expensive dam and a large extent of land to go underwater, and therefore, so compared to these things, I would say large hydro, they will go something like say $3 million per megawatt kind of, or even more, because there are a lot of relocating people cost, building new houses for them, and there are a lot of involvement. So, therefore, large hydros have much higher, we call them specific cost, per megawatt cost, we call them specific cost, much higher specific cost, and the same are here in Indian rupees million, but the Indian rupee amount changes depending upon the exchange rate. Better to remember in dollar terms. So, roughly have an idea with you, small hydro development costs somewhere between 1 to 1.4 million rupees to develop 1 megawatt power plant. Then you can know something about how much is wind, how much is solar. So, as electrical engineers or technical technologists, you must be able to have a comparative idea with like a doctor knows medicine, as engineers we should know our subject area. So, if somebody asks you how much will be the cost of a 1 megawatt small hydropower plant, you should be able to say it might be around 1 to 1.4 million dollars per megawatt, depending upon the location and also the specific requirements of that particular site. So, as we all know, hydropower has a very long history. If you take wind or solar, maybe last 20-25 years, right. Earlier there may have been pilot project of solar or wind, but no commercial projects. But if you take ever since electricity was invented, immediately afterwards hydro turbines and generators were connected and hydropower plants were set up. So, I have been to some large hydropower plants in Norway, huge size, and I visited one power plant 300 megawatt into 4 Pelton units. One Pelton unit was 300 megawatt. So, I have a picture taken with the spare turbine, huge turbine. And China has not recently, about some 10-15 years back, they have commissioned almost the world's largest hydropower plant, 20,000 plus megawatt, one single plant in 3 Gorges Dam, and they are huge. So, hydropower has a long history and also it is a very much proven technology. And so they have been a very good reliable renewable energy supplier at economical prices. You know, electricity from renewable energy projects are long standing. Even small hydropower plants will run, if implemented rightly, with the correct technology, they will run 20, 30, 40, 50 years with the same turbines, maybe a little bit of refurbishment, but they are long lasting, and you can always run for many hundreds of large hydropower plants. They have run hundreds of years. Maybe you replace the turbine after 30, 40 years, but still all the other components are good enough, and therefore they have a long life. But if you take a wind power plant, maybe 10, 15, 20 years maximum, then you have to throw out everything. And if you take solar power plants, their guarantees are only 20 years. So, after 20 years, you have the formidable question, where to throw the solar panels, where to dump them. So, but in hydropower, you do not have any such problems. So, hydropower, therefore, out of renewable basket, hydropower plants stand as the much better option. Therefore, all these power plant options available in India, more than 15,000 megawatts must be implemented, giving preference to them over solar or wind, which are not as good as mini hydro, because mini hydro has the other advantage, they have higher plant capacities, plant factors. Plant factors. Normally mini hydros have plant factors above 35, some running into 40, 45. Whereas, if you take a solar power plant, plant factor will be about say 20% without tracking, with tracking maybe 25%. So, therefore, their economic life, the economic benefit returns are lower compared to small hydropower plants. So, the small hydros are as old as the large hydros, because they have implemented them everywhere possible. For example, in Europe, they have started with hydro turbines, not for electrical generation initially, but directly for grinding their crops, etc. And later on they shifted them to be connected to the generators. Right. So, in our countries like Sri Lanka, India, small hydros were first introduced in our countries by the British. Both countries have been European colonies. So, in their time when they grew tea and rubber, etc., to get electricity to their bungalows and factories, they installed mini hydropower plants because they were mini hydros were available invariably in the tea estates and so on, where the highlands are located. And therefore, in Sri Lanka also and India also probably there have been very old mini hydropower plants installed by British in 1950s or even earlier. But as the grid growth to the remote areas, they abandoned the mini hydros because grid power was more reliable and much cheaper, and they did not want to maintain mini hydros. So, they were given up. That is before 2000. But by the time year 2000, world energy prices increased to go up. Oil prices, which were conveniently below $20 a barrel before 2000, rose above $20 a barrel and went up to 30, 40, 50, 60, 70. Today it is about $70 per barrel. Therefore, the energy cost has risen significantly, and the result is now old abandoned sites as well as new sites of mini hydropower are very commercially viable at the present day electricity prices. Therefore, they are developed in Europe, in Americas, in China, in Asia, in South Asia, in our countries, because everywhere most of them are commercially viable and supplies reliable electricity to the grid operators. And so, hydropower projects fall into two main categories. They are storage schemes and run of river schemes. Storage schemes, as we all understand, we will see the slides and then go on, right. So, run of river schemes, as the name suggests, they use the water running in the river and utilize the water to operate the impart the energy to a turbine, and then directly put water back to the river. There is no water storage, water collection, and therefore, these projects are much more environmentally viable and environmentally less polluting or less interfering compared to large hydropower plants. And this small hydropower, which might be pico hydro, micro hydro, mini hydro, whatever the name suggests, 95% or even over that are run of river power plants, no storage reservoirs are there. But there are few mini hydropower plants, as we will see in later chapters, later discussions, have been developed in existing dams, and the new dams have not been constructed, but in existing dams there have been hydropower plants developed to utilize the energy potential. So, there are about very few, maybe 3-4% number of small hydropower plants connected to reservoirs. That is not because reservoir was made for the mini hydropower plants, that is because reservoir was available, and therefore, that was utilized to create a mini hydropower plants. Otherwise, all small hydropower plants come into run of river category. We will see what is run of river in more details if you did not get the full idea in the later slides, where I will be discussing with some diagrams. One issue with run of river power plants is that you can't carry water from wet season to dry season. That is the advantage of having a reservoir. You can collect water during wet season and preserve it, and then utilize that water to generate during dry season. So, that facility is not available with run of river power plants, but that facility comes with a huge environmental impact of the large hydropower reservoir, where you keep the water collected, which has been flowing perennially over thousands of years downstream. Now, you stop everything, collect it in your reservoir and use it as you wish. So, which is a huge environmental intervention, and that ecological system, all the animals, trees, and even people who are downstream are severely affected. Therefore, in the present day context, large hydropower plants are not thought of as environmentally friendly power plants, other than the benefit of not releasing greenhouse gases. So, even large hydros have the advantage, they do not release greenhouse gases, and therefore, they are considered as environmental friendly, but the ecological impacts of large hydropower plants are sizable and presently thought of as not very environmentally sustainable. So, and another advantage of run-of river power plants are they can be built, that without much expert knowledge. You do not have a reservoir control, you do not have to build a reservoir, therefore, they can be constructed, these power plants can be constructed with local engineering knowledge, and also they have better long term reliability. And so, they are very environmental friendly, and downstream flow patterns are not affected, and there will be no appreciable upstream flooding. When you block a river and prepare a dam and collect water, backwater level. So, if you construct a dam and collect water, right, your backwater curve, right, earlier river was flowing at this level, now you raise the water level, therefore, the river's water level, backwater level will go up in the upstream to some maybe few kilometers, and the lands adjoining the river previously not flooded will now be flooded permanently because of the formation of the reservoir. So, all the maybe crop growing people will have maybe tea estates, rubber estates, so other farmers will be affected by the lands newly going under water. So, that is also an environmental impact of having a reservoir connected to a large power plant. So, they are having issues. So, as I said earlier, small hydropower projects are almost always run of river type. So, I will be using the word, as I said earlier, small hydropower projects for all the power plants starting from say 5-10 kilowatts up to say 25 megawatts in Indian context. And so, the storage schemes, right, they have a water collected on a large reservoir. So, the advantage is this water can be used during the dry season when there are no rivers, no rains, but the small hydropower plants will operate only with the rainwater available. But when I say rainwater, it is not necessary the rain to come every day, because the catchment areas where the water is falling will have certain water retention capacity. If you take a forest, when the rains come, the certain water goes under the soil, and then they will be released slowly as fountains later on. So, even if the rains are not there, there will be water available in the river for some time, and by that time again the rains will come. Therefore, there is a sustainable way of doing it, because even if the rain is not there, these small hydropower plants will still operate, of course, with some reduced capacity if the water level goes down slowly. So, the storage schemes are more complex and expensive because of the reservoir, and they will face the problem of silt accumulation. In large reservoirs, if you take the reservoir over the long term, there will be the silt accumulated in the reservoir, and the reservoir's water capacity will gradually go down. Therefore, either you have to remove silt or otherwise your water retention will be lower and lower. This is especially happening because of the lot of agricultural activities in these areas, which will let lot of silt to flow and to end up in the reservoir bottoms. So, therefore, these are negative impacts of large hydro. So, on in all we can say large hydropower plants, although they can give a big capacity, have number of issues due to the involvement of the reservoir, and therefore, they are not thought of as environmentally sustainable, environmentally friendly projects in the present day context. Here, if you didn't get, some of you didn't get the idea of run of river power plant, here is a typical diagram which I will be referring from time to time during this course. So, this gives an idea about what are the components and how we do plan small hydropower plants. So, we can see in the blue line the natural water flow in the river. So, river flows in its natural course, right, and goes down, and there is a height difference. This is a hilly area from this point to this point, there is a certain height difference, maybe 50 meters, 100 meters, 200 meters, 500 meters, depending upon the location. So, that is what we are going to use. We are going to use the potential energy of water at the high altitude converted to electricity. That is the purpose of a hydropower plant, whether it is a large hydropower plant or small hydropower plant. Small hydropower plant, we are using simple components compared to a large hydropower plant. So, here we have identified the height, and we have identified the location where the water can be diverted, right. So, here we have identified the location for the powerhouse, right. So, there are number of choices. You can put a penstock straight from here to here, steel pipe. Somebody might argue, okay, why not? They can do, but that is not the way that we do it. We will explain why it is so. So, we normally take water through a low pressure canal or channel to a convenient location closer to the powerhouse. So, we can make the penstock as short as possible. We will have a discussion on the penstocks later, but penstocks are expensive on one hand, because it is usually steel. Penstocks are expensive, right. Therefore, if you do it this way, it will be much longer and more expensive. And on the other hand, when the water flows through the penstock, depending upon the penstock diameter and the internal resistance, there will be internal losses. We call them head losses in technical terms. Therefore, longer penstocks have longer head losses. Therefore, the electricity amount you can generate from this penstock, long penstock, will be lower, comparatively lower by the short penstock. Therefore, we want to bring water to a convenient location on a canal, and then start the penstock from there to keep the penstock as short as possible, right. So, there are a number of terms we use for this canal or channel, right. So, we use it. You can see there are some overflow canals here, and also another one here, and then we can see there is a tank here, what we call the forebay tank, right, where water, why we will see later why we need the forebay tank, and from where the penstock will start and will be connected to the turbines here. Here we can see the turbine, and then we can see the generator here, which are coupled together and which will produce electricity, and that will be connected to the grid. So, it is a typical configuration of a layout of a small hydropower plant, which is operated on run of river basis. You can see we are using the same water. So, when we divert water, we will provide some major water component to the canal, but we will release some water into the river as well, what we call the environmental flow. To keep this river section from A to B, again we do not want it to be dead, right, without water. So, the environmental investigations of the project will reveal how much should be the simple Q, depending upon the nature of the project, right. Therefore, when you obtain the environmental approval from your whatever the environmental board, they will check how much water should be released from the diversion point to keep the river live, so that the river, trees, plants, animals in that river section will not die, right. Therefore, the water which diverted will be go through the power plant and come back here. So, the affected part of the river is only A to B, that is also having without detrimentally affecting it, because we release the environmental flow. Q is called the environmental flow or the minimum flow, right, which is determined by the environmental investigations. So, therefore, these small hydropower plants are having a minimum environmental impact, right, because we want to keep even the affected river section live, So, we can see the other components of the power. So, we will be in this course, we will see how to locate this location, why not here, why here, why not upstream, right. So, we will see some ideas on that. So, when you have to identify them, and then how many overflow canals we need, and what should be the slope of the canal, because if you use more slope, your head will be less. Therefore, typically the slope of a canal will be about 1 to 1000 typically. So, that is 1 millimeter per 1 meter length, right, 1 millimeter, that is enough just to water to flow. We want just to water to flow in the canal. It is not necessary to have any pressure or any speed, much higher speed, right. We want just water to flow and come to the forebay tank, come here, and from there onward water will speed will pick up in the penstock and provide the necessary pressure for the turbines to operate. So, really the head will come from here, top water level to the turbine level. We will discuss these terms head and so on later. I am just indicating the sizes here for as an introduction, but we will see these things in more details as we discuss in the future topics. So, in Indian context, here are some steps that if anybody is, if you are joining a company and the company wants to develop a small hydropower plant. So, these are the steps that you should follow, your company should follow for the development of project, right. So, identification of or selection of the SHP site, that is something that we will discuss in this project, and then evaluation, you have to evaluate to see whether it is viable, and submission of a pre-feasibility report, right. So, to this extent the knowledge required we will be discussing in this course. So, with this knowledge you gain from this course, you should be able to prepare a pre-feasibility report in order to make an application to the whatever the authority that you are you should be submitting the proposal, and then obtaining the no objection certificate or clearance certificate by the developer, and submission of detailed report, grant of techno-economic clearance. You know, we have to do some economist has to do a techno-economical viability check. So, some estimations are required, what are the benefits coming out of the project, and some estimations are required, how much will be the total cost of the project, and then you must do a cost benefit analysis and see whether it is economically viable. Then signing of the implementation agreement, and most importantly signing of the power purchase agreement. Sometimes you have heard these terms PPA. As engineers, electrical engineers and engineers, we must be familiar with these terms. Every power plant is having a power purchase agreement signed between you and the utility or the utility in that area. So, a power purchase agreement will give the long term, maybe for 20 years, usually they are for 20 years. So, every hydropower plant, every solar plant, every wind power plant, every private power plant has a negotiated or standard power purchase agreement between the developer and the utility, and therefore, you must know what are these things. You can have a look at typical PP. We are not discussing about PPAs in this course, but you can download, there are sample PPAs in the net, you can get them and have a look at. But as an engineer, if you join a private company or government company, whatever, doing renewable projects, right, private investments, then you must be familiar with power purchase agreements, because invariably you will have to discuss these things with the utility, whoever the your network operator, and then discuss the terms to the advantage or the mutual advantage of developer or your company and the electricity utility that you are going to be connected to. Then the funding arrangements, you will have to talk with the bank and talk with your company, how much we can put. The bank's investment, we call it as a loan or debt, that we have to talk about loan or we call it debt. And then investors contribution, this is coming from a bank, and investors investment, what we call equity. This is the developer or your whatever the company that you have. So, usually for hydropower plants, this is about 30 to 70%, equity 30 and debt about 70%, but it can vary from 80-20, 60-40 depending upon the various other financial conditions and risks associated with the project. And then arrangement of the equipment and manpower, you have to discuss with suppliers who can supply the best equipment for my project, and then the construction, completion and commissioning. So, these are the steps involved in a small hydropower development if you are joining a small hydropower developing company. And of course, in this course what we learn will be useful for you to do the pre-feasibility study and to see the financial viability of the project. And contour maps, right? Contour maps are very useful in understanding and designing and identifying small hydropower projects or even large hydropower projects, right? And I forgot to tell you, in large hydropower projects, this canal usually in renewable energy, small hydropower projects is the equivalent counterpart of the tunnel. I am sure in large hydros you have heard about the tunnels. So, the tunnel is the low pressure tunnel doing the same purpose, going on a very low slope, bringing water to a convenient location to make the penstock shorter. So, in a large hydropower plant, the function done by the canal in a run-off river power plant and small hydropower plant is done by a canal in large hydropower plants, a tunnel in large hydropower plants. So, understanding this canal or tunnel path, right, is facilitated by the contour maps. Contour maps will guide you how you should route, how is the route of the canal, how the route of the tunnel should be designed or planned. And then contour maps can be used to identify what should be the better location for the water diversification, right? Water diversification, that is, using the contour map you can see where should you start this diversification, water diversion, right? So, contour maps will be helpful. And then where should be your penstock be placed, that will also be facilitated by a contour map, and where the power plant should be, because the power plant should be placed so that in the flood season this water level will raise due to floods. So, your power plant should not be inundated, otherwise your equipment, control equipment, generator will be going under water, and this should be then in technical terms we say it should be above the 100 year flood level, right. So, how to identify those things we will discuss in the coming topics, right. Therefore, contour maps will facilitate identify all these things. Therefore, development of small hydropower projects or even large hydro projects, contour maps play a crucial role. Therefore, we will have a brief idea here about contour maps, and then we will during our discussion we will refer to them time and again depending upon the requirement. So, that contour maps can be 1 to 50,000, right, in general, and maybe in detail contour maps can be even 1 to 10,000 scale, right, 1 to 10,000 scale. So, the survey departments in the region, maybe in your Indian case your state survey departments normally publish covering the entire state. These days all the areas are covered by these maps, because they have a lot of technologies now, satellite technology and so on, and therefore they can take images, satellite images and so on. So, they have very accurate contour maps, right. So, but sometimes in some areas they may not have produced 1 to 10,000 detailed map, because they are not required. If it is a huge forest area where no development activities are taking place, probably they may not have produced 1 to 10,000 maps, because they are not required. But when the development activities are happening, these maps are really useful, right. So, a contour map shows lines of representing equal heights on the ground with the heights indicated level above the mean sea level. So, if you take a hill, right, say if it is say if the sea level is here, right, you can say, so this circle represent height above the mean sea level, say 1000 meters, right, and the next line can say 1100 meters, and next line can say 1200 meters, and next one may be 1300 meters, top may be 1400 meters. So, you can plot the contour map, and this is 1000 meters contour map, this is 1100 meters, this is 1200 meters, this is 1400 meters, and top is 1300 meters, top is 1400. So, this is the contour map of this hill, right. I just took as 100 meters difference, but survey departments normally have say from every 10 meter gap. So, if they want, they can say 1000 meter, next one may be 1020 meter, and next one may be 1040 meter, and so on. So, depends upon the survey department who has chosen it, but in most cases they normally go by 20 meter contour heights. So, this is the hill, this is the contour map, that is the idea. So, you can likewise you can do to an entire region. If it is a flat area, say this is a flat area, right, contour map will be just one line, no other lines. So, it is 1000 meters, no other lines, because there are no other hilly areas, entire area is flat 1000 meters, like a playground. So, when you see a flat area like this in a map, you should understand when the contour lines are there and no other contour lines, you must understand that is a flat area, right, that is a flat area. So, flat areas are not good for hydropower development, because we want for hydropower a high difference between the water availability, so that you can use the potential energy of water to drive a turbine, right. So, if you see something like this, that is a flat area, something like this, that is a hilly area. So, this is good, this is not good for hydropower, flat areas, right. So, now we can look at a sample, okay, we will come to a sample map later, right. So, some information about sample maps, right. In addition to the contour lines is 20 meter height difference, main roads normally in red cover, by roads and cart roads normally in yellow and white color depending upon the authority. Usually these are British, even in Sri Lanka or India, I think the survey departments were first set up when the colonial rule was there. Therefore, they are usually uniform. The laws and rules and applicable in India and Sri Lanka are British originated. Therefore, these contour maps and other things are pretty uniform. So, normally they are in 20 meter height difference. You can investigate, go to your, I saw that in some of your survey departments you can freely download some contour maps up to certain accuracy. So, you can go and give your telephone number or something, mobile number, and get the authority and get download sample contour maps and see. And so, they also indicate rivers and streams, which is very important for us, because we are going to deal with the river or stream. So, every contour map has all the details of where the rivers are flowing, and usually they are colored in blue lines. We will see a sample only. And then the provincial boundaries, your state boundaries, all will be in the contour map saying this is the boundary between say Tamil Nadu and Odisha or whatever. The lines will be all will be marked, right. And the paddy fields, estates, tea estates, forests, all are detailed there. Then you can see from the map that these information are available, and many other information are contained in a good contour map. 50,000 scale maps are good enough for initial studies of small hydropower projects, while 1 to 10,000 maps are more useful in final designs. So, we will normally do the initial design with the 1 to 50,000 map, but after identifying the locations, maybe the canal path, maybe the forebay tank, maybe the diversion weir, we will get the 10,000 1 to 10,000 map of that location. That will give more details. So, that will help us to do the designs better, But I have done 2 projects, small hydropower projects as the project manager. I will show you some photographs if the time permits later. And but finally, before you really do the project, you will mobilize a survey team to the area, and they will make their own contour map covering the project area, because it is important, because these contour maps may have been developed some 20 years back, right, 20 years back, and by now the surface conditions may have changed due to landslides, maybe due to erosion, maybe due to human activities. So, the things may have changed. Therefore, in order to implement the project, normally the project team will mobilize a survey group who will do a fresh contour map covering the area that we are interested in. That is in the final stage, and that will be once the investment decision is taken, because that will cost money. So, we will do all these costly things once the investment decisions are taken. Until investment decisions are taken, we will do the pre-feasibility and other studies using the available plans, that is 1 to 50,000 plans usually available. You can pay a nominal fee and buy or download from the survey department. There are map shops where you can buy them from. And here is a contour map prepared for Sri Lanka by the survey department of Sri Lanka, right. So, they have this grid. So, for each of these grid cells, they have one map. This is 1 to 50,000 map grid, right. So, so each sheet has a number. I do not have the number here, say this they might say this is 61. So, I can go to the map shop and say I want to buy sheet number 61, because my project is somewhere here, I have identified. Therefore, I will buy the sheet number 61. So, maybe I can pay maybe $5 and buy a map, not that expensive, right. So, and also they have each cell point, they have expanded into 1 to 10,000 maps. So, it has therefore 5, right, 5, right, 5 into 5 maps, right, 25 1 to 10,000 maps prepared for each 1 to 50,000 map, right. So, even that is available, but that you can buy if you are really doing a project, identifying the final location where your project components are coming, right. So, you will not know the exact locations, therefore, you can't buy the 1 to 10,000 maps, then otherwise you have to buy an entire large bundle of 1 to 10,000 maps, which will be useless. First, we plan with the 1 to 50,000 map, and then we will try to buy the 1 to 10,000 maps. So, develop our own contour map depending upon the requirement. You can see even the covering the sea area, there are contour maps. So, not only hydropower projects, you are doing any kind of projects, even solar project or whatever, using a large area, like say if you do a 100 megawatt solar project, you will need about 500 acres. So, to know the topography, location, other features, it is always useful to buy a contour map and to mobilize into an area. Even if you are doing an agricultural project using a large extent of land, it is good to buy the contour map in that area, then to identify the land features, rivers available, and then the hills and other things, all the information will be available in the map. So, the contour maps are not only for hydropower development, they are for any activity you are doing as engineers. If you are mobilized into any area to do projects, it is always good to get the contour map of that location and to use them. Yes, I do not know whether the operators can open up the contour map I have given them. Can you open the contour map I have given them? Have you got it, or if so, please open it, otherwise I will go ahead with this. You can, if you can, good. We will come back to this slide later. If you can open the contour map, please do. kindly wait, they will open up a real contour map. I have taken them for Sri Lanka, but they are the same whether it is India or maybe even other countries. They will go from this PowerPoint to a picture file where a contour map is a 1 to 50,000 contour map is shown. The file name was Candy as I gave it, if you have not changed. Here you are. Yeah. So, this is a 1 to 50,000 map, right, make it larger, 1 to 50,000 map. You can see the features. Can you I do not know whether I can do it myself here. Yeah, I will zoom it a little bit. You can see lot of features are you can see from a contour map. Here you can see the red color main roads, and then the blue the rivers, right, and reservoirs, all the features are here, right. Green patches may be paddy fields, may be the location of other vegetation, and you can see here is a rocky area, no vegetation, and you can see even the contours are available here. That means it is a hill like rock, right. So, this is a contour map, 1 to 50,000 contour map, right. So, we will go and see a specific area of this map, so that we can be more familiar with the contour map setup. And you know, as a hydropower engineer, your eye must be used to contour maps, right. This is good for any engineer. You should be able to identify the land profile when you are doing any project in anywhere, right. So, the contour maps is a cheap option where you can identify the land profile, land features, etc. So, as engineers we should be able to read contour maps if you are really going to the field, right. So, I have used them in my life for different projects, like even for a large say solar projects. When we want to buy land, we first see whether the land is agreeable before buying the land. For that we will inspect several lands and look at the contour maps, their closeness to highways or the main roads, right. So, if you buy a land somewhere here, it will be much away from main road. So, if you are doing a large project, you will have to build your own roads unless there are existing roads available. So, depending upon the type of the project you are doing, if you have to do a heavy equipment transportation for your project, better to find the land somewhere it is closer to the main roads. Otherwise, you will have to build expensive roads. I am talking about any project, right. Therefore, the contour maps provide such information as we need for any project development, and they are a must for hydropower or small hydropower development. Can we go back to the PowerPoint slide again? Can close this and go to PowerPoint. Yes, here I have extracted a certain portion of that map, right, certain portion of that map. You can see here it is marked 900 here, right. Contour maps do not carry the numbers everywhere. So, you have to have some effort and find out. So, therefore, this hard color brown line is 900 meters above mean sea level height, and then you can see there is another brown line here. So, if I go along that, you can see it is 800 meters, that above mean sea level. So, in between, therefore, there is a 100 meter level difference, right. There is a 100 meter level difference between them, and in between you can see there are 4 lines or 5 sections, 1, 2, sorry, I will take the pen. Here you can see this is 800, this is 900. So, there is 1, 2, 3, 4. I press the wrong button, I think. 4 and 5 sections. Therefore, each section has a height of 20 meters. Each section has a height of 20 meters. Therefore, these light lines, in between there is a height difference of 20 meters. 20 meters, right. So, 800, 820, 840, 860, 880, 900, right. So, you can identify that there is a uphill here. You will have to climb uphill, and then it goes to further. You can see that I can't see the number, and then this brown line must be 1000 meters. In between there are 4 lines or 5 sections, 20 meter each. So, you can see it is again going uphill, right, uphill, right. And then you can see there is a river flowing here, You can see this is the same line 800, this is 800 meters, right. And then if you take another line below that, so this must be 700, this line, right, in between 800 and 700. So, it is going here 700. And now we can see strangely between this river point and this river point, how much is the height difference? There is a 100 meter height difference, and the water is flowing, you can see this way from high altitude to the low altitude, right. So, we can see between this point and this point, if you want, we can put up a hydropower plant with a 100 meter head, right. That is how we identify hydropower opportunities. But if you go further down, there is another line here which must be below 700 by 20 meter. Here is another line, this may be 680, this may be 660, and so on. I am just not putting the exact numbers, you can find out later, but I just put some tentative values. But from the important point is, from contour maps we can identify where hydropower plants can be developed, where the hydropower opportunities are available, where the height difference are available with water flow, right. So, you may have never been to this site, right. We have done some projects in Uganda. In Sri Lanka, we have invested in I worked in some company called Windforce Private Limited. We invested in 2 hydropower projects in Uganda. So, we did not know anything about that land. So, we got hold of contour maps first, and without ever visiting the site, looked at opportunities and identified, right. But now we have implemented a 8 megawatt project and it is in operation, right. So, that is how you start the project. So, even in India, you can identify potential sites and then see whether there is already a power plant constructed. You can go to Google Map and go to the site and see whether it is already there is a power plant. If there is no power plant, you can propose. All these you can do in office without going with the new technology, but the real power plant development you will do later by visiting the site, etc., right. So, you can see that there is a road here, the main road, right. You can see the kilometer marks are also there, 164, 63, 62 and so on. So, you can know the distances, all these things, and there are, you can see this white color, this is a by road, this is a by road going from this one, you can see. And then there are this is a higher grade road, not red light, this may be B grade, this white one may be C grade roads. So, you can identify what are the roads available near your project. If you identify this as a project location, it is good that you have a B grade road close by, right. Then you can go, if you want to make a site visit, you can go along this road and park your vehicle here and then have a walk here, right. So, your site visits all you can plan, right, with the help of contour maps. Therefore, contour maps are helpful in numerous ways in developing hydropower plants. And we can see this black color broken line, that must be a provincial boundary, right. and so there are many other, right, many other information available, and there are small rivers. You can see this hairline like small rivers, right, they are coming and joining the main river, right. And also remember, rivers flow, when the rivers flow, contours are like this. So, the river flow is this direction, right. So, when you stand along the river looking at the flowing water, your hands like contours will be like this, the hands like in this way. So, you can easily identify which way the rivers are flowing. So, this is flowing this way therefore. Otherwise, sometimes you get confused which way the rivers are flowing, this way, with the contours are like this, right, and same way you can identify. We will look at these things in details in later topics. This is just to get familiar. Here I have marked a possible way of identifying the river location. So, you can see in this particular river there are contour lines like this, you can see, and their heights are marked. So, I have selected to tap water here, diversion weir, right, and then take water along this canal to a location here where the 4 bay tank is located, right. I told in the previous discussion that normally the contour has canal has a very low slope. So, normally about 1 to 1000 as I said earlier, but exact amount you can calculate using a different formula, but roughly about 1 to 1000. So, that means you go almost parallel to a contour line, right, almost parallel to a contour line, because contour lines are lines of equal height. So, you need only 1 to 1000, that is 1 meter drop for every 1 kilometer. Therefore, you will pan your canal very parallel to contour lines, right, and then come to a convenient location, and then your penstock should come cutting many contours, because that is where the slope is. When contours are cut, between every contour 2 lines there is a 20 meter drop, 20 meter height difference. Therefore, your penstock should come cutting many contour lines in a short distance. That is where your head, your water flow pressure comes in. We want to keep the penstock as short as possible, right. So, that is the idea. So, I have put the powerhouse here. This is typically how you plan a hydropower plant using a contour map. Identify a contour location, basically how to develop a hydropower plant. Then there is a concept of how much water can come into this diversion point. That is a good question. So, that depends upon the rain upstream. Then all the rain will not come to it, it come to certain lands above this point which are sloping into the river can collect water into this. So, this gives the idea of catchment area. So, this is called the catchment area. When you have a catchment area, you have to identify the catchment boundaries, that is which area has the potential of water that coming in the rain can have a chance of flowing into my diversion point, right. So, I have marked here the catchment boundary, this is the catchment boundary, right. How to mark it I will discuss in a later topic, right. So, water in this area falling in this area can come to it, but water coming here will not come into our catchment. It will go to this small river and water will go to some other part, that will not come into our river, our diversion point. Therefore, it is important to identify what is your catchment area. If it is a small catchment area, maybe you will not have enough water in the long run. So, a project therefore must have suitable amount of say area as catchment area. Typically, for a high head project like 200 meter head project, catchment area will be 10, 15, 20 square kilometers. But if it is a low head project like say 20 meter, 30 meter head, maybe catchment area may be 200 square kilometers, depending upon that. We will discuss these things a little bit in detail later on. Okay. Now, we will go to the second part of this lecture, right, that is identification of hydropower development opportunities and locating the diversion weir for a given project. So, with this background knowledge that we have already acquired, let us see how to do it in a more precise way when there are number of opportunities, which one is better and how to decide on that, right. So, as we said earlier, this is a typical layout that we have been looking at of developing a run of river type small hydropower plant, right, run of river type small hydropower plant. So, now the components we are little familiar. We have a diversion point, or we call it diversion point, intake or weir, or there are a number of words that we are using. Here is another new term that we didn't discuss earlier, settling basin. Settling basin, we will discuss about settling basin in a little more detail in a subsequent topic, but settling basins are required because from rivers we get silt and sand. Silt and sand flows in rivers, amount depends upon the type of the river, right. So, silt and sand, when it comes, if the silt goes into the or the sand goes into the penstock, what will happen? It will go and damage the turbine, right. It will go and erode the turbine, and thereby turbine will be destroyed. Therefore, we want silt to be taken out of the canal or the tunnel or whatever we are using before the water enters the penstock. So, for that we are using a settling basin, or sometimes we call it desilting tank, desilting basin or desilting tank, right. We will have number of them, maybe at the initially if the river carries lot of sand, if the river water is always brownish, that means it carries sand and silt, right. So, we will have one at the intake and remove silt as much as possible entering it, but we will have, if the canal is long, say 1 kilometer long, then we will have another in between, and we must have one here at the forebay tank. A desilting basin at the forebay tank is a must, because something can fall in here from top and then it can be carried to the penstock. Therefore, we will have number of desilting basins right upstream depending upon the length of the canal, but we must have a desilting basin right at the forebay tank, enter to the forebay tank, to avoid the possibility of any sand going and entering the penstock, right. Why then somebody might ask, why we spend desilting basins at the upper side? We can have one final desilting basin here rather than spending money and having desilting basins in the middle and up. What happens is, when silt enters here, it gets deposited in the bottom of the canal, because the canal flow rate is not very high, it is a very low slope. Therefore, over the time silt fills, right, and then the canal height shortens, then the water cannot flow now, right. Therefore, it is important no silt accumulate in the canal. That is why in long canals we need couple of desilting tanks in between also, that depends upon the river condition, the silt level, etc. Therefore, normally when we go for the first inspection, we will take couple of water samples and see how much silt is there, especially in the flood season, and thereby plan accordingly the desilting basins, required number of them, because they are having a certain cost, but we will try to minimize the cost as well as minimize the possibility of salt depositing. Here I have selected another contour map. This is slightly different from previous one. This is from another country. This is 1 to 63,360, but that survey department has selected this, right. So, it does not matter the type of curve, whatever the one that you get, we can use. It is a matter of the height difference and the details available, etc. So, this is a little expanded one I have selected. We can see contour heights are given in these are all in meters, right. You can see here it is 200 meter, 200, 250, 300. So, you can see between these numbers there is one line here. So, therefore, it must be 300 and 350. So, this must be 325, right. So, now in this particular map, between any two lines height difference is how much? 25 meters. So, it is a different scale used by a different survey authority, right. So, you will encounter many such small differences. The previous one, the height difference was 20 meters and here it is 25 meters. So, about the details it will be different, and when you do your own contour map for the site using a survey team, you can ask him, I want 10 meter height difference, or I want 5 meter height difference for my scale, because in order to plan your civil device, civil components, you might need that detail, right. So, we can see, so this particular map, and we can see that some river system here, this it is not blue in this particular one, these are rivers, and there is another branch also coming and joining, and there is another river system here, branches coming and joining, right, river system. So, and these both river systems come and join at this point B and make a larger river, right. Now, this is given to a hydropower engineer like you, right. Now, you are going to be a hydropower engineer. So, given a hydropower engineer by your company and said, okay, see whether we can develop a hydropower plant, or whether there are a number of options, so one option or whatever, you are asked to look at this and give your opinion, right. So, now you look at, so then when you look at, you can see, because we know for hydropower, I will come to this formula later, but for the for your benefit I will mention the power, we will discuss this later on. Power developed from a hydropower plant is equal to efficiency into Q rho G H. Rho and G we know, rho is density, G is gravitational constant, we are familiar with. Q is the flow rate, H is the height difference, or what you call the head, right. Q is flow rate in cubic meters per second, H is in meters the water head height difference between your diversion weir and the forebay tank level and your turbine level, right. So, that is what we are interested in hydropower, what is the height, potential energy is in the height. So, we want to convert that to, so you can see it is the power is, this is in watts or kilowatts, right. It is directly proportional to Q and H, flow rate and head, right, flow rate and head. Now, with this in mind, now the hydropower engineer looks at this. So, he first looks at the river system, this river system, what you have marked as A, he look at this, and then he thinks, okay, I will get tap water here at point A using this river system, right, and take it parallel to a contour line, this is his canal, right, canal, and take it to point A1 using a canal. So, here will be the forebay tank, right, forebay tank that we looked at earlier, right, and then I will have my penstock from A1 to C. C is near the river, little above the sea, so that the flood level is not exceeded, and at C we have the power plant, and that is the hydropower scheme. And we can see B1 is at 275 level and powerhouse is at A1 is at 350 level, A1 is at 350 level, C is at 200. So, that power plant has a head of 150 meters, right. So, that is a project, right. So, whatever the water come into this play QA will be available for power generation. So, his power plant will have a output of, power plant A will have output of efficiency into QA rho G into H, H is 150 meters. Q will depend, Q you can't put a value, it will depend upon the rain conditions and the water available upstream, the flow of that day, right. So, Q is a variable, therefore, it is not a constant value. Q will go up and down depending upon the time of the year, time of the day, right, depending upon the water availability in the river, right. And then your colleague suggests, you are looking in a team, your team is looking at this diagram now,
your colleague suggests wait, if we go to point B, we can increase our Q. Why? Another river comes and joins us, right? Another river system comes and joins us at B, this river. So, our Q will be therefore naturally larger, but of course, we will lose some head because it is at a lower height, right. Therefore, he suggests shall we look at this option also. He suggests we tap water at B, take water along this canal to B1, which is at 275 contour height, and then locate the power plant at the same place C at 200. But now, our power plant has a head of 75 meters only, 75 meters only, but Q at B will be larger than Q at A, right, Q at A. So, there are two options now. From the same map you have extracted now two information, right. Then which is better, that we have to decide on economic terms, which project will bring better financial returns will be the project to be selected, right. That we have to design the project, we have to look at the two projects compared and do a cash flow analysis and to see which project is financially more attractive. That is how we take the decisions in the field. So, here is a summary of the two projects, right. So, in option 1, diversion weir is at A, canal path A to A1, right, canal path A to A1 and penstock A1 to C, powerhouse at C, right, powerhouse at C, head is 150 meters. Same way, if we have the point B as your diversion location, B to B1 as the canal, B1 for bay tank, penstock B1 to C, power plant at C and head of 75 meters. But now, this option 2 will have a higher flow because two rivers have joined together, right. So, I have summarized them here, I do not want to read it again. You can see final line I will read, decision will be based on better economic returns. So, you do it and your financial controller or financial accounting department, they will do a cash flow analysis after you do the preliminary pre-feasibility and estimate approximate costs, and approximately how much energy you can generate. Those things we are going to discuss in the future topics, how many gigawatt hours or how many million kilowatt hours you can produce every year. That is important because that is what you can sell, right. And then your plant will have a certain cost, your diversion weir or dam will cost, your canal will cost, your forebay tank will cost, your penstock will cost, your powerhouse will cost, your turbines and generators and the other electrical equipment will cost. If you have a step up transformer, that will have a cost, and if you have an interconnecting line, transmission line, that will have a cost. So, you can add them up together, that will be your total project cost, right. So, total project cost versus amount of millions of kilowatt hours you can estimate to be generated every year, that is you can sell. Then you can do a cost benefit analysis and see whether plant A or plant B is the better option. That is how when you do the things in the field. But we in this particular course we will not discuss about cash flow analysis and other things because of the time limitations, but you can use a accountant or a financial analyst to do those comparisons. So, you can see now here, now once you have interested in this, you need to know, right. Now, your boss will ask you, now you have looked at these options, now you are telling there are two options. What is the capacity of these two options? How many kilowatt or how many megawatts each plant is sizing? And now you have not been to the site, you do not have flow data, but your boss is asking how many megawatts each project. So, you can't say I do not know, right. So, you can make a best estimation from this, right, still in the office. Maybe this location may be some other country. Right now, you have to answer your boss question. How much is the megawatt capacity for project A and project B? Right? Very difficult, of course, but you have to give a positive answer. Right? Then you get hold of other information. Now, you have to know how much water will come to point A for my diversion. How much will come to point B? Right? We have to know. Then you can at least have an average idea. How much water comes, then you can divide by the number of seconds in the year and say per second this much can be expected. But for that you must know how much water is coming to your diversion point. How much water that will come to your diversion point depends upon how much water will come into your catchment area, and therefore it depends upon rainfall as well as the catchment area. If the catchment area is large, rainfall is large, you can expect more water. If the catchment is small, less water. So, therefore, you need to mark the catchment area in this map. So, let us see how it is done. You can see point A, the catchment is marked by this line, you can see. That is the catchment for project A. Now, see how it has been marked. Right, you can see water flow, I said contours are like this, right, contours are like this, right, but you can see this is a hill range, this is a hill range, you can see this is a hill top, this is 500 meters, you can see 400, this is 500 meters, this is also 500 meters. Therefore, you can see we have made a fictitious line here that divides the hill range, this way another slope, this way one slope, right. And here also you can see there is a hill tops, and water into this river system goes from here to there. If the rain falls here, that water goes into this river system. If the water falls here, water goes into this river system. And also incidentally we note that in contour boundaries, contours are in the other direction compared to the contour shape in the river, right. Here also you can see. So, you can use this all these knowledge in marking the contours, the contour catchment area boundaries, rivers this way, contours this way, and other hilltops you have to approximately guess, but the criteria is you judge whether rainwater falling at that location, whether that can come into your river system of interest or whether it can go to the other river system. Here we are looking at the project A, therefore, we are looking at this catchment area. So, if the water falls here, we know that cannot come into our system. So, that goes to this river system, therefore, that cannot be our catchment area, right. So, always argue whether the water falling there, rainwater falling there can come into your catchment area or not. If it cannot come, that part cannot be your catchment area, right. So, this is initially difficult, but when you are accustomed to, you can gradually learn, right, how to mark the catchment area. So, once you mark the catchment area, right, if you know the rainfall in this area, say annual average rainfall is 1000 millimeters, then you know annually how much water is coming into your catchment area. Suppose your catchment area is 20 square kilometers, right. Catchment area is found to be 20 square kilometers and the rain is 1000 millimeters, so 1 meter. Therefore, your catchment has a water reception of 20 kilometer squared is 10 to the power 6 meter squares, right, into 1 meter, that is 20 into 10 to the power 6 cubic meters are coming into your catchment, right. I am just putting random numbers here, right, just to understand the principle. So, we are sure that you can get on average about 20 million cubic meters into your catchment area, but there is no guarantee that this will go into my diversion point, because in between lot of things happen. Some water will be evaporated, some water will be soaked into the soil, some water will be taken by the trees, right, and so on. So, only a portion of that can come into my diversion point, right. Let us look at some more slides describing this. Here you can say rainfall map, you can from this you can, for any country there is a weather stations marked. So, you can get the rainfall data from the closest weather station to your site, that is one way, right. And also there are maps like this, rainfall map for Indian city states also there must be. You can see on a scale it says on average how much rain can be expected. You can see in Sri Lanka there are very wet areas, this you can see here, you can expect about 5000 millimeters per annum, right, water. But there are some dry areas, you can see very dry areas, this is less than, right, 1000 millimeters, right. So, you can see, so with this kind of map, if your location is somewhere here, if your project is located somewhere here, catchment area is here, you can approximately get, it may be 2000 to 2500, you can approximate 2250, because we are doing an initial estimation, because your boss is asking the question, right, how many megawatts. So, you are trying to find a solution on a reasonable scientific based solution, right, because we are doing an initial investigation. We can go to the site, get river measurements and all these things at a later stage, but this is an initial look, right, initial look. So, once you know this, you can calculate, as I said earlier, this one. But there are, if you are lucky rather than using these maps will be very approximate, but if you are lucky, you can give a call to these weather stations and check where is the nearest rain gauge to this site. You give the coordinates of your site and ask them where is the closest rain gauges, where are the closest rain gauges to this site, right, and then they will say there is one at 10 kilometers away, another at 25 kilometers away, another at 50 kilometers away. At these locations they might say 1 or 2 or 3 or 4 rain gauges close by to your catchment area. Then you can get the average of that, right. You can call them and get the annual rainfall and get the average of those 4 rain gauges, rather than going by this approximation, because these are very rough, but actual measurements will be much better, right, actual measurements will be much better. Therefore, so this is the worst case, we use this, but if you are lucky we can find close by rain gauges. So, I have here marked, you can see for project B, for example, for project B I have marked the catchment area. You can see the project B is this one. So, the catchment area is like this. It includes project A also, because the water in project A also come into it, right. So, this area I have separately drawn here, traced it to a separate diagram here, same catchment area. So, project B is somewhere here, diversion point is somewhere here, right, B, right. So, I want to know the areas now. So, I have got the area, and the weather stations told me there is a rain gauge here W1, they told me there is a rain gauge here W3 and a W2 rain gauge here. Now, one way is getting the average of them, but they are at different distances. So, it is not very reasonable. Therefore, what I have done is I have marked a triangle here, because there are 3 weather stations, weather station 1, weather station 3, 2. I have marked a triangle here and then bisected the sides, Now, I can divide my catchment area into 3 areas. I can mark this portion of the catchment area is more represented by W3, it is closer to that, and this segment of the catchment area is more represented by W1 weather station, and this area is more represented by W2 because these areas are pretty large, remember maybe 100 square kilometers, right, 100 square kilometers. So, therefore, now I have got a good estimation. Now, I can calculate what is the area here. Area calculation of a catchment area is not difficult, even if you go to Google map and give the boundary, it will calculate the area for you. There are softwares you can use for catchment area calculation, you just have to give the boundary, right, when the boundary is given. So, when you give this boundary, there are calculators, you can calculate how many square kilometers. Now, I have got the information, right, I have got the information. This line is wrong, this line should come here, right. I have got the information, right, that you know at weather station 1 rainfall is W1 meters per year. Here the rain gauge weather station 2, it is let us say W2 meters per year. Here W3 meters per year, that is the average annual rainfall, right. So, I have got that information, and therefore, I will say my average rainfall is, right, average rainfall for my entire catchment I can calculate. For example, this is one way of doing it. Average rainfall is, right, water will come this area is AW1, I have put square meters, right. So, AW1 into W1 plus area W2 into rainfall in W2 plus area W3 into rainfall W3 divided by the total area W3, right, which will give me average rainfall that can be expected in the total area, total catchment area, because I got 3 rain gauges. If I got 2 rain gauges, I can just bisect it and get it 2 areas, right. If I get only 1, I can use that. Since I have got 3, I have put that sample here. So, I have put here some typical numbers. W1 is 2500 millimeters, so I have put them in millimeters. W2 3200 millimeters, W3 1800 millimeters. Area WK1, sorry, area in the AW1 3 square kilometers, AW2 12 square kilometers, AW3 8 square kilometers. So, now you can get the average rainfall, right, rainfall into area, rainfall into area, rainfall into area divided by the total area 2621 millimeters, right. So, that is in my catchment area average rainfall is 2621 millimeters as per the 3 weather stations that are available, right. So, I can depend upon this number to some extent, right. Now, I told you that all the rain that goes into this will not come into my diversion point. Why? Because the water will be evaporated, trees will transpirate it, trees will absorb and leaves will transpirate it to the air, and some water will go to the groundwater, right. Some water will be utilized by the people, animals and so on. So, only portion of it can come to my diversion point, Therefore, you know that people have developed a graph like this, rainfall runoff graphs, right, rainfall runoff graph. So, you can see the vertical axis is rainfall, horizontal axis runoff. What does it mean? If the rainfall is so much, how much will go in the river? Now, for example, here, right, if the rainfall is here, let us say this is 1750, runoff is 0 almost. What does it mean? If the rainfall, annual average rainfall is this low, river will be dry almost, right. But if the average rainfall is say 3500 millimeters, then your river will carry approximately say 2300 corresponding to 300 millimeters of rainfall will be flowing in the river. And this previous calculation showed us our catchment has the average rainfall of 2621. So, I have marked it here 2621 and corresponding runoff is 1200 millimeters, right. Therefore, now I can calculate how much water comes into my catchment, right. My catchment now corresponding to 2600 millimeters rainfall is 1200 and my total area of the catchment is AW1 plus AW2 plus AW3, which happens to be 3 plus 12 plus 8, that is 23 square kilometers, right. Now, I know water volume coming into my diversion point, right. Water volume coming into my diversion point is catchment area A into rainfall. This is the water volume at diversion point, right. So, that is in this case 23 square kilometers. I will convert it to meter squared by multiplying by 6 square meters. Rainfall is now 1200 millimeters or 1.2 meters. So, now this will convert to be the amount of cubic meters of water is coming to my diversion point that can be taken in for my power plant use, right. Of course, you will have to minimum flow a little bit you have to reduce, but let us forget there is no minimum flow. Therefore, now we can calculate, right. So, it is 1200 millimeters into 23 kilometers squared. Now, I divided by the number of seconds in the year, 365 days, 24 hours, 3600 seconds, right. So, when you multiply all these things with cubic meters and seconds, you can get average flow rate as, right, 0.875 square cubic meters per second. Now, we have a Q value, right. P we know efficiency into Q rho G H, right. H for the project B is 75 meters. Now, we can put this value efficiency into Q is 0.875, rho is 1000 kilograms per cubic meter, G is 9.81, H is 75, right. So, we can now calculate the project capacity, right. Efficiency normally total efficiency for the project we will see later on how it can be calculated, about 75%, right. So, you can put something like 0.75. Now, you can see you come with the project like 552 kilowatts project B, right. So, with these numbers I have put some random numbers for areas and rainfall etc., but exact numbers you will get when you are doing a real project, right. So, you can now tell your boss one project is having 550 kilowatts. Same way you can do it for the project A, right, and say project A has a capacity of this much, right, and then now you have answers, right. But this is very approximate, remember, which you can do when you are doing initial investigations from your office with available theoretical knowledge. It does not cost you anything other than your working hours, number of working hours. But if it happens to be 50 kilowatt, then you will say there is no project, we will forget about it, right. It is a very small, no point company doing a 50 kilowatt project, right. But it since 500 kilowatt, it definitely there is a project. So, the further investigations are worth doing, right, further investigations worth doing. So, this is how you initially identify project locations using a contour map, right, project locations using a contour map, right. So, it may be in some other country, it may be in some other state, right, you have never visited, but using the available literature available data, you can do an initial investigation and see whether there is a project where it is worthwhile to do further investigations, right. So, in this lecture we have discussed about our initial concept of small hydropower compared to large hydropower, what are the advantages of small hydropower, and also initial concept of using contour maps for project identification. And we said that what there will be a water diversification. Usually small hydropower plants do not have tunnels, instead we use a low pressure canal or channel to bring water to a closer location, so that we can keep the penstock length shorter and the penstock cost lower, and then develop the project in an economical way. And also we looked at how we can do initial investigation of a project location, whether there is a sufficient capacity, initial estimation of a sufficient capacity. And with this we can go further and make further investigations and develop the project, which will be discussing in future modules of this course. If there are any questions, we can take up now, or otherwise I will give when I have extra time, I will give some other time slot, common time slot, where we can discuss about further questions you may have. If there is an immediate question from online participants or from you, I can take it and spend a few minutes. Otherwise we will do it in a common slot where you can study it further and come prepared for clarifications of your own after your own studies, because sometimes this may be completely new to you. Therefore, you will need some time to digest the concepts and to understand yourself, and then develop the necessary knowledge and tools and other things for developing your skills in developing hydropower. So, I studied these things in late 1990s when my company, so I worked for a joint venture company between Norway and Sri Lanka as a general manager and the project manager also. That was funded by No Fund of Norway and another company of Trondheim Energy Work. They were the foreign shareholders, and in Sri Lanka it was Lanka Transformers Limited and another Sri Lankan company. So, they jointly invested in these projects, and so we developed two projects, a 4 megawatt project and a 2.5 megawatt projects in two different locations. So, I studied them separate, I studied and my other engineers, we teamed up, civil, electrical, mechanical engineers teamed up, and under my guidance we did these projects, and still they are in operation. They were commissioned in 2003 and 2004. Now, over 20 years they are in operation and no issues. We bought machines for the first plant from Germany and the second plant from India, and from that gentleman I was showing you Kerala investigations, he was the one, the company is weir near Delhi. So, we purchased for the 4 megawatt plant machines from them, and for the 2.5 megawatt plant we bought from a company called Folk Wasserkraft WKV, a German company. And both machines are good because weir also in India they produce under German license. Original company is German, but under their license they produce equipment, and I think in India there are many small hydropower turbine manufacturers. So, I think we will conclude there, and there is another session maybe in the afternoon, we will meet up there. Okay. Sir, what is that? Rho, yes, yeah. The question is what is rho? Rho is the density of water, but this equation we will discuss later how to obtain this. Q rho GH, this is hydropower equation for large or small hydropower. In a future module, we will discuss how to derive that equation, right? Mathematically, how to derive it, we will discuss later in some other slide, some other module, right? Under the same course, right? You will encounter it later. So, we will conclude there for today. Right. Okay. Thank you, and see you in some other module. Okay. Testing, testing. Okay, we will start our discussion on mini hydropower plant design and integration with DC microgrid, and the present topic is identification of hydropower development opportunities and locating the diversion weir for a given project as a extension of a previous discussion. So, The objective hydropower scheme is to convert the potential energy of mass of water flowing in a stream with a certain fall to the turbine, termed the head, fall is termed the head, into electrical energy at the lower end of the scheme where the powerhouse is located. The power output from the scheme is proportional to the flow and the head. So, the equation for the power generation, which we will be looking at a later stage, efficiency into Q rho G H, where Q is the water flow rate, cubic meters per second, H is the head of the project, G and rho are constants, rho being the density of water, G being the gravitational constant. So, development of a hydropower project means finding a Q and finding H. So, we earlier looked at classification of small hydropower projects based on the capacity, pico, micro, small hydro and large hydro and so on. But there is another classification based on the head called high head project, medium head projects and low head projects. High head projects are generally 100 meter and above as the head H, and medium head ranges from 30 to 100 meters, low head 2 to 30 meters. You can see even 2 meter head can be a viable project. You can see that as per the power equation Q rho G H, when H is small, H goes down, Q need to be high. Therefore, these small head projects are really handling in large rivers where volume of water is high, but the drop is small. When the drop is small, H is small, but since the Q is large, maybe 30, 40, 50 cubic meters per second, then power is good enough. And present day there is another category called ultra low head projects. Ultra low head projects that less than 1 meter head. So, they come in large rivers across which dams are built for multi-purpose, and you can create about 1 meter head, and that on that we will see some configurations in the coming up slides, that you can embed turbines and generators within the dam itself, so that there will be a series of turbines and generators along the dam generating power. So, I have seen similar power plants in large rivers in Germany and so on, Rhine river and so on. So, they have built dams and embedded large series of turbine generators which are generating electricity. Because Q is high, they can be of sufficient capacity. So, cite this classification based on head. You will hear these terms in the industry. High is that a high head project, medium head project, low head project. Cost wise and development easiness wise, high head projects are the number one. So, in a country when mini hydropowers are developed, first they begin with high head projects, because they are straightforward configurations and economically more viable. Then you go to medium head, and once you finish the medium opportunities also, you go to low head projects. So, in low head projects, the civil components are fairly big, civil structures are fairly big, therefore, a little bit more expensive, because large volumes of water have to be dealt with. You have to have wells and other things where they need to handle big quantities, Q. Maybe Q may run into say 50 cubic meters per second. You can think of how to handle that, 50 cubic meters per second. So, to civil structures will be fairly big, inlet valves will be fairly big, and the piping and other things will be fairly big, although they are short. Since the head is small, penstock equivalent part will be short, that is true, but the diameter will be huge, because you have to handle 50 kind of cubic meters per second kind of flow rates. So, schemes are run-off river schemes that we looked at in the previous session, and schemes with powerhouse located at the base of a dam. So, in this here we are looking at some configurations possible for implementation of hydropower in various other forms of opportunities, not in hilly areas where you have high yield opportunities, but other opportunities, and also schemes integrated on a canal or in a water supply pipe. We will look at some of these site configurations. So, as we know, run of river schemes are when where the turbine generates electricity as and when the water is available and provided by the river. When the river dries up and the flow falls below some predetermined amount or the minimum technical flow for the turbine, generation ceases. So, every turbine has a minimum requirement. For example, if you have some kind of turbines, at least there should be 10% of the flow, rated flow, or 20% of the rated flow sometimes. In some turbine types which we will be discussing later, you need at least 30% of the rated flow to start generation. If when you do not have that flow, you have to shut down. So, hydropower is like that. Hydropower, some turbines cannot work with very minimum flow. You have to have at least some guaranteed amount to begin the generation. So, medium and high head schemes are schemes use weirs to divert water into the tank. It is then conveyed to the turbines via a pressure pipe or penstock. Penstocks are expensive and consequently this design is usually uneconomic. An alternative is to convey the water by a low slope canal running alongside the river to the pressure intake or forebay, and then on a short penstock to the turbine. That is the general configuration of a high head project, high head to medium head project. If the topography and the morphography of the terrain does not permit the easy layout of canal, a low pressure pipe can be economical option. You know, we when you instead of a tunnel in a large hydropower project, we use a canal. We use a canal, usually a concrete canal, to bring water from the water diversion location to the forebay tank. That is the normal option. But sometimes, you know, to bring this tunnel is very difficult. Build this tunnel is very difficult because of the terrain. Terrains are very slopey, or maybe the soil is so loose, and therefore, the construction of a concrete canal is difficult. In such cases, people use, you know, low pressure pipes, which are not necessarily steel pipes. They may be FRP pipes, you know, fiber reinforced plastic pipes, FRP pipes, right, which can be used as a instead of a canal. Sometimes they can be economical also, and they need not to carry any pressures. It is just water flow. Therefore, we can have instead of a canal, a low pressure pipe as well. Right. So, and as usual, we release the water back to the river at the end of the power plant over to we call the tail race. Here is a high head scheme, right, high head scheme, a schematic view. It shows the elevation and the plan. So, when you have a cross sectional view, you can see small weir. We do not want to have a big pond, because when you have a pond, there will be a backwater increase and inundating other people's land boundaries. So, we want to keep just enough diversion, so that the water enters the canal or the channel, right. So, water enters here, right, on the side of the dam, and then it is brought, right, and you can have a tunnel or a canal, right. So, you can see if you look at the plan view, here is the pond, the water is diverted into the, right, into the, so water normally flows this way in the river, and now water is diverted using the weir or the dam to a canal, and the canal runs this way, right. And in this particular project, they have opted for a tunnel when they encountered the hill, right, that is an option. But if you find tunneling is not possible, we can go around the hill. Again, the tunnel can be extended to go around the hill and come it, right, because the tunneling is not very technology is not very abundant in this part of the world. But if you go to country like Norway, they are experts in tunneling, right. So, I have travelled up and down in many parts of Norway. So, now they do not have winding roads when they are going in hilly areas, right. They do not have winding roads to go up and come down, they straight away go through the hill. So, there are hundreds and hundreds of tunnels in road network of Norway and maybe in other countries also, right. I have seen whenever you travel you go through many tunnels, because the tunneling technology is advanced. There are many subcontractors and service providers where if you ask them they will come and have the tunnel done. And also they are these hills are very rocky, suitable for tunnel building, not like loose soil, right. So, they are both advantages. So, in those countries even for mini hydro they use this kind of a tunnel rather than using a canal, right. But in Sri Lanka, for example, if this opportunity comes, they would have opted for this, going around the hill with a extended canal, because that is cheaper and you do not have to have the tunneling technology. But in this particular project they have opted for tunnels, right. And then you have the forebay tank, right, and penstock and the powerhouse and the tail race. Tail race is where the water is released back to the river. So, this is an option you can see when you have an opportunity, right, when you have an opportunity. And in the low head scheme they are typically built in river valleys, right. Two technological options can be selected, either the water is diverted to a power intake with a short penstock as in the high head scheme, or the head is created by a small dam provided with sector gates and an integrated intake powerhouse. We will see some of these things diagrammatically. Here is a low head scheme with still with the penstock, same arrangement, right, same arrangement you can see. So, here is the reservoir and usually in any powerhouse, whether it is high head, low head or medium head, whatever, we have in addition to the desilting basin will take out sand and silt, right, it will take out sand and silt, but not the floating objects like leaves and logs and other things, that will not be filtered out. So, you need a trash rack, here is a trash rack, right. So, trash rack is a mesh, right, mesh, and the mesh size depend upon the particular turbine. So, if something is going in, it should be able to go out, right, without blocking, right. So, that is the criteria. We will look at the criteria of designing this later, but anyway it is a mesh. So, things will be accumulated here. So, in Europe etc., it is expensive for them to have people here. Normally a man will stand here with a long stick or something and he will drag them out and take out onto this and remove it. In Sri Lanka there are many people employed this way, trash rack, at the trash rack, right, at the in the forebay tank, where they continuously clean, right, whatever the falling leaves and other objects. But in Europe I have seen they use automated trash racks. So, there is a machine which will come every 5 minutes or 10 minutes as programmed. So, they will program it to be more frequent in the season of leaves falling and all that, and it will just come here and drag everything up and go on doing it many times, right. Automated trash racks are there, right. Okay. So, anyway then the clean water will come in here just like any other, and the penstock is here and the water flows through it, and you can see this shaft brings out which is connected to the turbine here. Turbine is here at inside. So, it is connected to this shaft and shaft is connected to generator. Generator is in air, right, turbine is there. So, there is a water seal here where the axle comes out or the shaft comes out, right, and connected to the generator. And these turbines are, we are going to discuss turbines later, types of turbines. So, these are called reaction type turbines, right. So, the other type of turbines are the impulse type turbines, which we are going to have a separate discussion under different topic, right. and here the issue is, the problem is not the problem, the characteristic is the head is considered as the top level water level and the downstream water level. The head will be this, right, downstream water level and the upstream reservoir water level. So, that will be the H. But if you take a high head scheme where the 4 bay tank is there and you take out the pipe and the water comes and hit the turbine, then the water jet comes and hit it. So, the head will be top water level in the 4 bay tank and the jet level, water jet level, not the tail race water level, right. That is a high head project using impulse turbines, right. But here in a reaction type turbine, usually I am sure you have heard this word, Francis Kaplan machines are reaction turbines. So, they are fully immersed in water and the applicable head is lower reservoir water level and the upper reservoir water level, the difference, that will be the head. In the impulse type ones, for example, Pelton turbines or turbo turbines, it is the jet level to upstream water level, right, head. So, this is possible in existing dams, existing reservoirs, etc. And also the head will be medium or low head, right, but the Q will be large, therefore, you have a sufficient capacity. Right? Okay. Here are some other configurations, you can see the elevation here, right. There are gates, etc., right, and then the trash rack cleaner, and you need sometimes fish passes for the environmental reason, right. And then you can see here the section AA, right, here the powerhouse generation section AA, right, here you can see here is the powerhouse, right, this is the generator and this is a vertical axis configuration. So, in hydropower plants you will see both configurations, horizontal axis configuration as well as vertical axis configuration. Especially in large hydros, it is a vertical axis arrangement, because if you have a horizontal axis one, the weight of the generator, weight of the turbine, etc., will be too much on the shaft, because they are very heavy and shaft might deflect, right, Therefore, in large hydros, usually it is always large hydro machines vertical axis configuration, but in small hydros you can go for both, it is a design option, right. Horizontal axis is always a cheap option, right. So, but this is due to this particular arrangement, they have opted for vertical axis configuration. Generator is up here, so it is axis here, right. So, this is the axis. So, this is a Kaplan turbine. So, water comes through the trash rack, enters here in this chamber and then goes through the turbine. Turbine blades are here, right, and goes out, tail race, right. So, it is a Kaplan is one version of reaction turbines, They can be used in any configuration suitable. There are power plants which are having a penstock and then ending up into a Kaplan turbine, but the penstock will be slightly bigger, because and also it is low pressure, because the penstock they have low head means low pressure. You do not have to have expensive steel penstocks, you can have a FRP pipe, fiber reinforced plastic pipe. Right. So, they are available now commercially for hydropower development. They are fabricated in many parts of the world, especially in Europe, and they are economical compared to steel penstocks. They are much more economical. So, in Sri Lanka, I have seen several power plants which use FRP pipes as penstock material, right, penstock material for low head projects under similar conditions, right. We have your head may be 20-30 meters, right, even less. So, in that case this configuration is good, right, and also these materials. So, these are in addition to developing high head projects, right. Earlier we looked at high head projects where you have hilly area and then you have the contour lines to get the various heights, and then develop a project with a diversion weir, canal, canals may run into 1-2 kilometers. I have seen projects 1 to 2 kilometer long canals, and the penstock can run into 1 kilometer, right. So, they can be that long, as long as the economic sense is there, they will do the project, right, they will do the project. But these are very short, these are short and in a small area. You do not have kilometers long canal, maybe 20-30 meter long penstock, because the head is small now. You do not need naturally long penstocks, but the diameter will be large. I will show you some when we discuss penstocks. We will see how some of these FRP pipes are used in low head schemes. I will show you some photographs. But they have their own disadvantages. You know that once we had the problem, we had I was managing a company and we had a low head power project done in Sri Lanka, and it was in operation, but we found that water was leaking. The penstock was buried, and penstock was FRP pipes, right, and buried pipes, and then we found it is leaking inside somewhere, and also that soil is coming inside, right. So, we immediately stopped and opened up the that buried areas and looked at. Then we found that pipe is damaged, and we later learned that now gradually people have used to use the area, because of this covered area for various purposes. Among other things, heavy bus has been coming that area and has been turning at that point, because that was an open area. So, the bus have been constantly coming, stopping there and reversing and turning everything on this pipe buried area, and that pressure was too much, and that damaged the pipe. So, we had to replace that portion of the pipe. So, if it is a steel pipe, that would not have happened probably, but since this is a FRP pipe, you have to be careful when you bury it, etc., and not to have people going there and doing various activities with heavy equipment, and the pressure might damage the pipes, right? Pressure might damage the pipes. So, here is a existing dam, right. How to build a small hydropower plant, that water release from existing dams and reservoirs. So, I have seen similar opportunities in every reservoir. There is a irrigation, even in powerhouse power plant system, there is a irrigation outlet, because you have to release water for irrigation purposes. Even if you collect water for power generation, irrigation release is a must, right. So, they have a pipe at the bottom, right. So, water is just released. So, I have visited one of the power plants in Sri Lanka and given a proposal some time back how to insert. You can, so, in the same pipe you can insert a machine, you can just cut the pipe and insert a machine in between, right, machine in between, so that the pressure, you can see there is a head here, you can see H, right, Q is here, that is what we want, right, that is what we want, right. So, you can generate electricity constantly, otherwise wasted energy, right, otherwise there are a lot of similar reservoirs in Sri Lanka. Now, in a few already there have been power plants inserted, in a few of them already power plants have been constructed, right, and more on the cards, because now the energy is expensive and high head opportunities and medium head opportunities are not there. Therefore, it is more beneficial to engage these things in existing reservoirs. Maybe in India also there may be many hundreds of opportunities, maybe the 21,000 estimate by the Indian government, this kind of things are not included yet, right. You go for this kind of things once you are exhausted with, you have exhausted all the existing high head, medium head projects, right. First you utilize them, and because they are more economically viable, and when once you have no other opportunities, you can go for all these existing dams and other things, where you can just insert a machine in a already existing water release pipe, like irrigation releases or drinking water releases, or whatever other ways of water releases for other needs than power generation. Power generation water will be taken by another intake through a canal or a tunnel to the same system that we discussed earlier, right. This is in addition to that, this power generation is in addition to that, the regular power generation. So, if you have a water canal, okay, open canal running water, right, because the water flows because of the slope, So, you can insert a machine, you can see here you can see you have taken this section is developed, this is the canal, normally water is flowing, right. In a normal canal water is flowing, water flows because of the head, we are going to use that small head. So, you can, of course, you need to keep a bypass when the machines are in maintenance and other things, you will have to close this section, power plant section. Therefore, you keep a bypass to be used in maintenance times, etc. Otherwise, you put water inside and your turbines, etc. here, generator are here, and then release water back to the same canal. So, you can have number of them, right, number of them serially along the steep section of the canal, or these are maybe probably man-made canals in irrigation schemes, right. But you know that in the coming years, when the energy is going to be more expensive and we need to go for renewables, etc., will pressurize people to go for even 100 kilowatt, 200 kilowatt kind of applications to be developed, as that because of the high prices of energy, they become economically viable. Therefore, a company will come and say they will sign an agreement with the irrigation department, in all these canals we will install turbines wherever the opportunities are, and they will pay a royalty to the irrigation department for utilizing their water. They will say 20% of the earnings from this scheme we will give to irrigation department, right, and the balance we use for our investment. So, the irrigation departments also get an additional income, right, by leasing out their canals to be used for hydropower generation. So, these are the models coming up. It is happening in already Sri Lanka. In Sri Lanka, there is a river called Mahavali river, and where very large power generation projects have been developed already. So, therefore, there is a authority called Mahavali Development Authority, and so they have many irrigation schemes. Now, they have allocated or leased sections of those rivers like this to mini hydropower developers who have put their money, invested their money to develop projects, and they are paying royalty to the Mahavali Development Authority, right. That is a negotiated one, but the owner has a power purchase agreement with the electricity board, and he sells energy to the electricity board, get the income. Out of that, 10% may be going to the irrigation authority or Mahavali authority or whoever the owner of the irrigation canal. So, it is a successful model, right, it is a successful model. So, these are opportunities other than the high head projects. We are discussing other opportunities other than the high head projects where we can develop small hydros, right. Here is a now sometimes ancient dams etc. are not very attractive for for doing construction work, for archaeological and historical reasons. So, if you propose to drill them or cut them or insert pipes inside them, archaeological departments and irrigation, whatever the other religious institutions, others will be extremely opposing doing any construction activity inside the dam, because they are 1000 years old. In Sri Lanka also there are dams which are 1000 years old, right, 1000 years old. Therefore, no one wants to touch them, right, no one want to touch them. Therefore, what happens is we can have this siphon action. I think as you might have experimented that if you fill this pipe and let the water flow, it will continue to flow because of siphon action. So, initial water flow you have to do with some pumps, employing pumps, you have to initially fill water by keeping the end closed, right. You can keep this side valves closed and then fill water, right, fill water, and once it is done, water started to flow, it will continue due to siphon action, and you can keep a turbine and generator here. So, you are not touching the existing dam, right, you are not touching the existing dam. So, this will be preferred in ancient reservoirs having archaeological value, where due to historical reasons no one want to dig into them to do the construction, right. So, these are also on the cards in the future when the we don't have opportunities for hydropower new projects. So, these are the final options. Okay. So, I have allocated the balance part of the today's discussion to answer any questions that you may have, right, answer any questions you may have. Also, I would like to add a few more points. So, you can I do not know how the online people will communicate from any part of the discussion we had today. You can if you have any questions, you can raise questions now. Otherwise, I can ask a few questions from you, so that to know that you have gathered the required knowledge. Yes, please. When she speak to the the microphone, is it recorded? That's recorded. Okay. Yes.
Good afternoon, sir.
Good afternoon.
It's been very informative. If at all, if we go with the calculation with respect to P, that is P is equal to efficiency into density into gravity into the length, height, sorry, then how we are going to fix that efficiency? You had shown up
Yes.
in the previous sessions that you have taken it as 0.75,
Yes.
that is 75%. Is that a constant or it depends upon any other factors?
Okay. Good question. That I will go to one of the previous slides for the clarity. Here you can see, efficiency in hydropower plants has many components. So, I would say efficiency is equal to, efficiency is involved wherever energy losses are there, right. So, the first energy loss will be in the penstock because of the friction and also due to bends, and there will be any other turbulences in the valves, etc. all will introduce loss of energy. When there is a valve, it will oppose water flow and some energy will be lost due to friction. If the pipe walls are not very smooth due to say corrosion, etc., there will be more energy losses. So, there will be first term will be the efficiency of the penstock, right, energy loss, and then comes the turbine efficiency, right. Turbine efficiency, I will show you a separate diagram, I will show you. So, because when the water hits the turbine, all the energy cannot be imparted to the turbine, some part will go out, right. There will be some water going out carrying energy, right. Therefore, the efficiency of the turbine, and then when the energy energy transfers to the generator. Sometimes there may be a gearbox also, if the speeds do not match. In some projects you have a gearbox, if there is a gearbox also there will be energy loss, but even if there is a direct couple, then you have the generator efficiency, right. So, the efficiency of the generator comes in, right, and then you might have a step up transformer, right, step up transformer to increase the voltage for transmission. So, you have a efficiency of the transformer, right. You may have a short transmission line or short or long transmission line from your power plant to the nearest grid point. So, there will be a efficiency of the transmission line, right. So, when I say 75% efficiency in general is the combination of these things. Sometimes you might not have a transformer, you might use the same low voltage, in that case that term will not come, right. Typically, if you look at efficiency of the penstocks will be about 95%, that is 0.95. I will skip turbines. Generator will be also, as electrical engineers we all know, generator will be about 96% efficient, present day generators. Transformers, if you see, present day transformers about 98% efficient typically, right. If you take the transmission line, again it may be 97%, maybe 3% loss if it is the transmission line alone, right. So, these are the, so why I skip turbines is, turbine is totally different. Turbine is totally different means, now even if the generator you take, from no load to full load, there will be a slight difference in the efficiency, right. But in case of turbines, this is not the case. Turbines full load to no load, huge difference in efficiency. So, I will draw efficiency curve here with the water flow rate and the efficiency for different turbines. We will look at the same when we discuss about the turbines separately, but because of the question I will answer. So, if you take a Pelton turbine, efficiency curve will be something like this, right, reaching out to almost say 93% efficiency, maximum efficiency of, right, if you take a Pelton turbine. But if you take a Francis turbine, the curve will be like this, right. So, this is the 100% flow rate, this is 50% and so on, 75%, maybe 25% flow rate, rated flow rate, right. So, you can see, so at part load say 50% flow rate, efficiency of the Pelton turbine is almost 90%, but if you take the Francis turbine, it may be say 75%. Part load efficiency is very poor. If you take a Kaplan turbine, it might be in between, right. If you take some other turbines like that there are turbines called pumps used as generators, they will be very worse, right. Therefore, when you use efficiency for power calculation as per our equation, right, turbine efficiency you can't put a constant value, you must see what is Q and select what is the efficiency and put that value. Therefore, this curve, complete curve you have to use, right. Using curve fitting technique, you have to make a formula or something, right, and then use that efficiency using exact efficiency corresponding to the Q. We do not have to do it for transformers and generators, etc., penstock, etc., because from no load to full load difference may be 1%, right, 1%, not very significant, but for turbines it is pretty significant. Therefore, we have to use the correct efficiency corresponding to the operating point. These curves you can get from the manufacturers, right. You can when you are buying equipment, you can ask him what is the efficiency curve, or there are typical efficiency curves also with the long experience. there are typical experience curves, but you can, if you search the net for turbine efficiencies, you will see set of curves like this, though that will give you the exact values, top values. Normally all types of turbines come to the maximum efficiency, about small hydros come to about 90%. Large hydros may even come to 93-94% maximum efficiency, but the part load efficiency depends upon the type of turbine. And also you can see Pelton turbines can start operations with about 5 to 10% flow rate, but if you take a Francis turbine, you must have at least about 20-25% of the water rated water flow available to start operations, otherwise the turbines cannot operate. So, there is a minimum requirement, but in that case the Pelton turbines are better. There is another version called turbo turbines, which you may not have very much heard. That is a recent development, recent mean about 20-30 years back. A British company called Gilks, they developed this technology, because Pelton turbine technology is 150 years old. They are very old technology, Francis and Pelton, but turbo was developed in 1990s, right, 1990s by this company. They had a patent for some time, but now they have many people are producing turbo turbines. So, it is something quite similar to Pelton turbines and impulse turbine. We will look at that when we discuss about types of turbines. I hope now you understand the efficiency matter.
Yeah, thank you sir, thank you so much.
Yeah, take the.
Hello, sir.
Yeah,
Hello, sir.
Yes, please, I can hear you. Give me, we will finish it.
Yeah.
Yeah,
So
please.
there is one question. So you have shown so many different designs of penstocks and models. So how they are actually affecting the power generation, and is there sometimes we say it is a load frequency control. So how they are managing it?
Can you Can you repeat the question? I got some parts of it.
Hello.
Hello, can you repeat the question?
Yes, yes, sir. Sir, you have shown so many different designs. So how those designs are actually affecting the power generation? Means which one is the better? And so that is the first question. And second question is, sometimes there is a load frequency control. So how these turbines and generators are playing role in that?
Okay, about different configurations, I must say it is rather location dependent, right, location dependent. So, an hydropower expert must visit it, and with his long term experience he must do the selection of the type, and not only that, the selection will finally depend upon the economics. You know, sometimes for a site, say Q is rated flow is say 5 cubic meters per second, right, H is 200 meters. Now, you have the option of going for 1 turbine or 2 turbines or 3 turbines or more, right. So, that is an option, right. So, going for 1 turbine might be bad sometimes, because if you have a large machine which is operating at low loads for long time, your efficiency will be bad. Therefore, if you have two turbines, they will be operating somewhere at a higher efficiency point, right. Therefore, having 1 turbine may not be the best option, but it has the advantage, you do not have to have so many control systems. If you have multiple machines, for each machine you must have control systems, generators, synchronizing breakers and everything. Therefore, finally, the final configuration we decide based on the return on investment. We do design 3 projects with 3 configurations and see which is bringing the highest return on investment, not on the economics. But other than that, there are technical issues in the construction. For example, if your location is far away from a good road, you have to build roads, and your road building is also expensive. Therefore, you do not build fully fledged roads, and if you have a very heavy component to be transported, then you will have to have very good roads and it will be expensive. Therefore, when you don't have good access roads to your power plant, you tend to have multiple machines. Then your cost of the weight of your largest component will be less. In a hydropower scheme, heaviest component is the generator. Right. Therefore, transportation of the generator is the issue. Right. If you look at the large hydropower plants, they do not transport the generator. They manufacture generator windings, everything separately, and build the generator at site. They bring the casing etc., because the casing is not very heavy. The heavy part is the core part, the iron core and the copper windings etc. So, they bring copper windings etc. part by part and assemble them at site. Turbine they bring at one unit, because turbine is not the most expensive part to transport. Right. So, therefore, the configuration and the final decision will be mostly based on the economics, return on investment. And your second part, you talked about some low frequency thing. Can you again repeat that part? I could not get it.
Just load frequency control, sir. LFC.
Yeah, for what?
LFC issue.
For what you mean?
Load they are coming in picture when the turbines and generators we are talking about. Also, there is something called Droop characteristics. So, can you explain? Actually, I am not put in what is the Droop characteristic. Now, you have shown there is a generator, this is a turbine. So, but when I see the block diagram.
Yes.
So, in the block diagram, where the Droop characteristics will come from these diagrams, what we have shown, sir.
Yeah, that is true. That the group settings and other controls will be decided based on particular governor characteristics. But small hydropower projects, we do not normally do the the frequency control or anything. These are normally operated at unity power factor and then connected directly to the synchronized directly to the network and generating the maximum possible, and we do not want to be sensitive or control the frequency, because these are 1 megawatt, 2 megawatt or less than 10 megawatt kind of machines. They are just connected to the network, and the network operators are not worried about the stability issues, because these are small machines. If it is a large machine like 50 megawatt, 100 megawatt, they will want to do a separate stability study as to how the machine will behave under different conditions. But for small machines, they are not worried about these characteristics. They just permit you to connect to the network.
Okay. Thank you, sir. Thank you very much.
Okay, welcome. Yes. Any other questions? Yeah, please, your question.
Hello. Hello. Sir, actually, if you allow me, I have two sets of questions. First question is, sir, this type of low head scheme, can we go for the multi-generator system?
Yes. So, I told you that, I have visited, I have really seen a project in Rhine River, where they have this, it's a very wide river. So, they have a dam here, similar setup, and on one side now water level is high. If you look at the cross section, I can draw it here, I will draw it here. So, water level is high on one side, other side water level is low because of the dam, and now they put a machine here, similar arrangement like this, and they put many machines, right. And in this particular case, they had a river pass, this boat pass also. Now no boats can go up and down when you have the dam, because there is a water difference now. So, they have a trap here, where the boat comes, and then you pump water to lift it up and then pass it on to the other side, right. And the reverse, when the boat goes to the other side, you go there and get it on the other side and empty the water and bring it to the other level and release it. because in those rivers lot of transport log and other transport activities happening. So, they need to have this flow, but when you have the dam you have the water difference, height difference, the boats cannot pass. So, they have to have a separate arrangement. So, there is a cost also, there water pumping etc. right. So, these things are there, therefore, multiple turbines are possible, and that is being done. I have seen projects with such multiple turbines, series of that, and these are the these things are done in the last part of hydropower development, right, because the head is maybe 2 meters or 1 meter, ultra low head projects, but the queue, enormous queue, right, enormous queue coming up. Therefore, P is high, you can have sufficient P power, Q, because of the Q is high. Okay.
Sir, next question is how to select, so many turbines are there, so how to select turbine type for low head schemes, what type of which is suitable?
That we will discuss discuss during our turbine discussion.
Okay.
So, there are turbine selection charts by IEC also has given, and manufacturers also have given turbine selection charts depending upon your rated flow and the head. So, sometimes you can choose multiple turbines types, then you can select it as per your option, but we will discuss about turbine selection charts at the appropriate point, right, in our discussion. Yeah, please.
Sir, in case of small hydro projects, that is for run for river scheme, under run for river scheme, you had described that channelized water will be fed via penstock to the powerhouse to generate electricity.
Yeah.
So, is there any concern taken about the pressure or flow rate of the water during summer season?
Yeah, during the summer season water flow rate will drop, and your generation will go down. So, you have to expect it, So, if you take if you expect can see the, if you look at a typical generation of a power plant in Sri Lanka, January, February, March, it will be low generation. Then April upward, it will be high generation, right. So, you have to expect this because you are fed by the monsoons etc. So, but what you are looking at the total generation in the year, sigma, right. So, that will, if that is economical, that create economic sense, that is enough, Now, in Sri Lankan context, not now, earlier once upon a time there was a tariff, feed-in tariff scheme where the rates were high during this period. We call it dry season tariff, and wet season tariff was a little lower. So, these are devices that to keep the people encouraged, and so that you get sufficient income to run the power plant. So, they gave two tariffs, dry season tariff and a wet season tariff. So, these are options the governments and the electricity boards can exercise to see this seasonal effect, right. So, in Sri Lanka we receive two monsoons, south west and northeast. So, different regions, different power projects get differently affected by the two monsoons. Some get both monsoons, some get only one. So, depending upon that your income levels will be different during different months. But for the economic calculation, we are looking at the total energy. So, we will be discussing that the energy calculation later, right, in a different discussion.
Thank you, sir.
Any other questions? Online participants also. You may even type into chat. So, I can take it up maybe at some other time even. When we have a spare time, extra time, I will extend the lecture and take up some of these questions in addition to the normal lecture part.
Hello, sir.
Yes, please.
Sir, I have a doubt in while you calculated, we had an average flow rate calculation.
Yes.
But then why did we go for the average flow rate?
Yeah.
The rated flow instead of going for the
Yes, yes, yeah, okay, good question. You know that average we do not build that, I agree with you, we do not build power plants for the average flow rate. It will be always little higher than the average flow we go. But this is, you know, we are doing from office an initial estimation to see whether there is a project. If with the average flow rate, if there is sufficient capacity like 500 kilowatt, 1 megawatt, then we know that there is a opportunity for a project. But you know, we never invest in a project with this average flow calculation, right. We will go for a once we are convinced there is a project, we will employ a hydrologist, we will employ a professional hydrologist to estimate daily flow rate based on 30 years backward data, right, and then ask him to project what will be the best average flow rates we can, average daily flow rate we can expect for the next 20 years. So, he will give a, you know, flow prediction like this. So, every month Jan, Feb up to December, and days, all the 31 days, right. He will say January 1st expected flow rate can be 1.2 cubic meters per second, and then 1.3. Likewise, he will give for the entire 365 days, right, 3.1 and so on. So, we will use this for the plant sizing, calculation of rated flow, etc. But that average flow calculation was to be done from office at no cost, just to see whether there is a project. But for this hydrological study and these things, we will have a separate discussion, right, how to do employ a professional hydrologist and get his report and use his data for the calculation of energy, and also a curve called flow duration curve. From this one we will have a separate discussion. That is the way that really we do it. But what I described this morning is only for initial checking of a site from office, once you have the access to contour maps and some kind of rainfall data. I hope I am clear.
Yes, sir. Thank you.
Okay. Any other questions? We have come to the end of our time slot. Okay, thank you very much.
Hello.
Hey Ananya. Ananya. ଝାଳ ଇଏ କଲେ ପ୍ରେସ୍ କଲେ ଖସି ଯାଉଛି ମୋ ହାତରୁ।
Good afternoon, everyone. Now we will resume the next session with Professor Monalisa Pattnaik from NIT Rourkela, who is going to deliver a lecture on design, development and coordinated control of a wind energy assisted.
Just don't talk about the topic.
So,
the topic ta कौन? Topic it is overview of microgrid.
Good afternoon, everyone. Now we will resume our next session with Professor Monalisa Pattnaik from NIT Rourkela. Professor Monalisa Pattnaik received her MTech and PhD degree from IIT Kharagpur, India in 2006 and 2013 respectively. She is currently an associate professor with the Department of Electrical Engineering, NIT Rourkela, India. Dr. Pattnaik is a recipient of POSCO Power System Award, Power Grid Corporation of India Limited, India in 2013. Her research areas are power electronic converter control, renewable energy systems, hybrid energy storage systems for EV charging, interlinking converter control in hybrid microgrid applications, electric vehicles and machine drives. So, ma'am, please proceed.
Thank you, Ananya. Good afternoon all. Now I am going to start the last session of this day. So, that is, as already in the first two sessions you have listened from sir, and that is purely about the mini hydro power plant design. But in my session and also Professor Indrajit Sarkar sir will be discussing about the microgrid part and its power electronics converter side. So, to start with, I will talk about the second part of this course, that is the integration of DC microgrid. But before going to the integration part, we will learn about the overview of microgrid and sizing analysis of energy storage system. So, in my today's lecture, this session, I will be talking about the what is a microgrid, the main classification of microgrid, the basic components of a microgrid. Then in the second part, I will talk about the what is the energy storage system and how it is required in microgrid, and with one example, the sizing analysis of energy storage system. So, in other classes, we will be talking about the power electronics part. So, today we are just
the basics I will discuss, which you may be acquainted with, but I thought I will start with this. So, as of nowadays this microgrid is getting very much attention, and to define a microgrid is nothing but a cluster of renewable energy sources, energy storage systems, load, various power electronics converter which operate bidirectionally when it is connected to grid. And this so here it can operate in a either islanded mode, or it can also operate in a grid connected mode. So, this the definition I have mentioned here, the microgrid is a cluster of multiple renewable energy sources. So, that is for a microgrid which contains only renewable energy sources, but there is a possibility of the fossil fuel based microgrid also. So, this is the layout I have shown here. This is the combination of the renewable energy sources as well as the fossil fuel based, that is the combined heat power based microgrid. So, along with the other the renewable source, the sources are here, and the storage, the load and the generator, means the components of the microgrid, each one by one I will be discussing. But it can, the one point I have mentioned here, the microgrid can operate in either in a standalone mode, or it can be operated in a grid connected mode. So, this is what, so but then I will talk about the advantages of microgrid. So, coming to the advantages, so this is basically I am talking about the renewable energy based. Due to the renewable energy source integration, it gives higher efficiency, higher reliability, as well as reduced carbon emissions and reduced per unit cost of energy. So, these are the major advantages for which we are now moving from the fossil based system to the renewable energy based microgrid systems. Okay. So, but so this is about the microgrid. It's then we will talk about the classification, how we will classify. So, before going to the total layout of the microgrid based on the different parameters, but means when initially we will try to talk about the what are the different types, means broadly how you classify microgrid, or based on which parameter you are classifying it. So, instantly we will say ki based on the power supply, whether it is there is a AC bus, it is connected to AC bus, then it is called AC microgrid. If it is connected to a DC bus only, then it is a DC microgrid, and if it is a combination of AC as well as DC bus system, it is a hybrid AC DC microgrid. So, this is about the configuration of a microgrid when instantly we are talking about. So, coming to the configuration, here in this diagram I have just shown the this again renewable energy based. I am not talking about the fossil based microgrid. So, all the sources here shown here are the renewable energy sources, but the sources are not, means I have not talked about in any of the figure. If you will see, I have not shown the this mini hydropower plant based, because till now as of now what I know, in India in normal scenario this microgrid is not, means in few places available, but mostly we are going for the mostly used renewable energy sources are the PV and wind, which are already available. And here if you see another source I have mentioned here, that is a fuel cell based source. So, that is the upcoming one which will come in few days, but so that is why I have made it dotted. Till now in the existing microgrids fuel cell is not available, it is still in the research state, and it is it is not very cost competitive. So, here first one, this figure shows the AC microgrid. So, all the sources as well as storage. So, what is the role of storage we will go next, but the sources storage are connected to the AC bus through its corresponding power electronics converter, and then the load for the AC bus based microgrid, means AC microgrid, if the load is AC. So, we do not need any power electronics converter, it is directly supplying to the AC load. But if you are supplying to a DC load, then we need another converter, power electronics converter. So, for the there is a corresponding conversion from AC to DC, and the in present state the upcoming load or the already existing this EV is going to be a very large, it is going to be existing load, so which need a charging EV charging station, so which is also mentioned for all the type of microgrids here. So for this again the role of power electronics I am not going to discuss, I am just discussing the based on the type of power supply we are dividing the microgrid into different types. So here first figure shows the AC microgrid which is connected to the AC bus, then coming to the DC microgrid which is so all the sources, the PV and wind sources, the fuel cell and the storage battery is connected to the DC bus with through the corresponding power electronics converter. So what will be the role of this power electronics converter? Here I am just including it as a black box, and whether it is a if it is connected to the DC bus and the source is suppose PV, so output is DC, so we are choosing a DC to DC power electronics converter. If the source is AC, giving AC output, that is wind turbine, so to connect to a DC bus we are choosing AC to DC power electronics converter, whereas here in AC bus system if you will see here the output is AC and we are connecting to AC, again we are using a back to back AC to DC, again DC to AC converter, because of the fluctuating nature of the this renewable energy sources, means wind and solar all are intermittent in nature. So and then comes the we will talk about the what is the role of storage. So this is the AC microgrid and DC microgrid, and correspondingly both can operate in the grid connected mode here, but when the DC microgrid is connected to grid it is through another power electronics converter, that is DC to AC converter. And again but here it is just the reverse, when I am supplying a AC load in AC bus system I do not need any power electronics, it is directly supplying. Similar is the case when I am supplying a DC load in case of DC microgrid, it is directly supplying the load, but when I am supplying to the AC load I need another power electronics converter, that is the inverter, DC to AC. So and each of the system in as of now the power system is AC systems, and now we are going towards this DC again, and each of the system is having its own advantages and disadvantages, and we will discuss that also. So when we will use the advantage of both the systems, that is AC microgrid and DC microgrid, we will combine the advantages and to form a hybrid AC DC microgrid system. So this is if you see this is just the combination of both the microgrid, AC microgrid and but the advantage here is we are taking, obviously we are able to use the DC sources and the AC sources, and correspondingly we are connecting to the corresponding buses through the corresponding power, choosing the proper power electronics converter. What will be the role of the power electronics converter, what are the configurations, topologies, that will be discussed in future classes, not today. I am just showing the type of depending on the type of supply you have to choose the corresponding power electronics converters. But when we are going for a we are getting more advantages here, we are combining the advantages of AC and DC microgrid, but as we are adding up two things, the system becomes complex due to the integration of both the AC as well as DC systems. Okay, so this is the basic types or classification or the configuration of the microgrid. Then based on the different parameters, so based on the different parameters I have mentioned, so one by one I will tell about the parameters. So based on the control, the microgrid can be a centralized type when a central controller makes the complete decision. So coordination and the maintenance here is easy, and it gives a better output or it gives a better efficiency. However, if there is a single point of failure, means if it is a centralized based system, centralized based microgrid, but if there is a common point failure, then entire system fails. That is the main limitation. Also it gives a limited scalability and reduced flexibility. So that are the major drawbacks of these centralized based microgrid systems. But when we are going for a decentralized based control, so that means each components can be controlled independently. So, they are independent of each other. So, in that case it gives a better control. So, it can be we need multiple controllers. So, efficiency means operation is better, but it gives it needs a complex design, and it is also complex to install and to operate. So, that is why that is complex. If you see means operation wise, the centralized type is easier, whereas the decentralized type gives a more complex operation and complex design. So, this is about the based on the control type of control. And then coming to the type of means the microgrid based on the power rating or the size. So, there are 3 types, one is small, medium and large. How we will categorize this small? So, if the power rating of the microgrid is less than 10 kilowatt, then we will say it is coming under the small size microgrids, and if the power rating is between 10 kilowatt to less than 1 megawatt, then it is falling under the medium size microgrid, and if it is greater than 1 megawatt, then it is falling under large size microgrids. Okay. So, this is based on the size or the power rating wise we are differentiating different type of microgrid. Then already this I have discussed, that is based on the power supply system we have AC, DC or hybrid microgrid. Then the another parameter is the type of source. So, source can be already I have mentioned it can be consists of fossil based source or renewable energy based source. Okay. So, fossil based source we are not discussing much here, because we are mainly focusing on the renewable energy based source. So, and when we are combining the both means we have the mixture of fossil based and renewable energy based microgrid, it is called the hybrid microgrid, means hybrid system having different sources, both fossil sources as well as the renewable energy sources. And under renewable we have the renewable energy sources that is already known to you: solar, wind, biomass, mini hydro, or it can be micro hydro, both are they are synonymous to each other, and the combination of 2 or it can be more than 2 also, it is called the hybrid renewable energy based system microgrid. Okay. So, there is a possibility of you can have solar wind, you can have wind biomass, or all the combinations together. But when you are going on adding the renewable energy sources, you are increasing, so complexity is also correspondingly increasing, but it is possible. So, but nowadays we are the sources having solar and wind, we are mainly working on these 2 complementary sources. So, forming the PV and wind based hybrid microgrid systems. So, this is about based on the type of sources. Okay. Then based on the type of load, so whether the microgrid is supplying to a residential load or it is supplying to a industrial load or the commercial load, we have 3 types of loading conditions means the microgrid can be. And the next one is the location based. So, it can be supplying to the microgrid can be located in at the remote locations, that is for the off grid operations also we can have these microgrids, or it can be for located at urban areas. So, that is also possible. And the last one is the based on the application. So, if the microgrid is for a military application, we can have different applications mentioned here: military, campus based applications, the communities, and for the districts or the islands. So, these are the based on the applications we are dividing the microgrids into these many types. So, this is the whole configuration, means the classifications of the microgrid based on the different parameters. Then again coming back to the components which I have shown in my first slide, that is for a renewable energy based microgrid. And so, the major 4 components again to clarify it. So, 4 components are the source, the load, then the storage What is the role of storage, then I will come to that. So, this renewable energy source, the load, the storage. So, storage are the what are the types. Here I have only shown two storages, that is the electrochemical storage, that is battery and supercapacitor, and sources I have shown just as an example. Other are possibilities, not that the other sources I have not shown here, but it is existing. Already I have mentioned the other sources of renewable energy, and the load can be the residential or domestic type, or it is industrial or commercial type. So, each unit or each component is connected through the to the bus through a corresponding power electronics converter. So, what are the types of power electronics converter possible? So, depending on what type of source you are choosing and whether it is connected to a AC bus or DC bus, and you have to choose the corresponding power electronics converters. So, like that is AC to DC, DC to DC, then again DC to AC is the inverter, or this is the back to back converter, that is AC to DC, again AC. So, here just I am giving you the introduction as a black box, means it is giving okay, it is the supply is DC, it is again it is as it is connected to the AC bus. So, it is the DC to AC means inverter. If it is the supply is AC and I am supplying to the means connecting to the DC bus, so DC AC to DC converter, like that. But what is there, the configuration wise we will see later. So, this is the how to choose the this what are the different possibilities, already I have shown there, but in a better way I want to explain. So, the sources which is connected to the AC bus, the all the renewable energy sources shown here, the storage are shown, the storage the battery storage is shown here, and the this is the domestic load, that is the smart household appliances, and the EV which is connected to the corresponding AC bus. That is possibility, I have shown the example as for a AC bus, and also it is possible that we can connect it to DC bus. So, for the as we are connecting it to this AC bus, and how to choose the corresponding power electronics converter. So, as for the first case solar, the output is DC, we know. So, we are choosing a DC to AC power electronics converter to interface to the AC grid. Similarly, for the wind power, the output is AC and we are connecting to AC. So, here it is directly shown AC to AC converter, but normally it is through a two stage conversion, that is AC to DC, again AC. In the previous slide also I have shown like that. Okay. And when I am interfacing a storage, the storage there has to be bidirectional power flow, means the storage will be supplying to the bus when we have load is more, means and generation is less, and the storage is charging, means it is storing when there is a more generation is more. So, that is we need a bidirectional power electronics converter here, but that is as it is connected to AC bus. So, we are choosing a DC to AC converter. So, basically I will be focusing on this bidirectional means the power electronics converter for battery energy storage system in my next lecture in detail, the corresponding design and all. And then coming to the residential load or the whether it is a EV load, we will choose the corresponding power electronics source converters, like the our nowadays household appliances are all are smart in nature. So, we need AC to DC, again AC to AC. Okay. So, that is a two stage conversion. So, as all the appliances are smart in nature. So, that is the inverter based AC, inverter based the washing machines we are getting nowadays. So, we need a two stage power electronics converter here. So, which is connected to the AC bus, and the last one is the EV load, which is we are supplying from the AC, okay, and this EV for the charging purpose. So, EV will be the battery, EV battery will be charged by using a, so first we are converting AC to DC, then the EV is charged through using a DC to DC power electronics converter. So, this is about, this is one example. So, same thing you can draw for a DC bus system. So, how to choose the corresponding power electronics converter type, means type wise, whether it is DC to DC, again same thing if I am drawing for a DC bus. So, this will be DC to DC converter. Okay. So, now coming to the other part of the components of the microgrid. So, that is the different local power generating units which I have shown as a renewable energy sources, but in another form we can define it as non-dispatchable and dispatchable. So, what do you mean by this non-dispatchable source? So, all the sources, that is the, you can say it is the renewable energy sources only, these RESs are coming under this non-dispatchable. Why? Because it cannot be controlled by the grid operators. So, because as you know these renewable energy sources are weather dependent, it is diurnal in nature. So, we have no control over it. Okay. So, these are intermittent, these are the problems with the renewable energy sources. So, the sources are already wind, PV, hydro, biomass, all we have discussed, but the this new the term used for it is the non-dispatchable power generating means sources of energy, and which one is called dispatchable, which we can means when we need, depending on our load requirement, we can make it on or off. Okay. So, that is called dispatchable source of energy. Can anyone tell this is what is the dispatchable? That is the diesel generator is one example of the this dispatchable source of energy. Okay. So, here in this table I have just given the examples of this different local generating units of microgrid, where I have shown this solar, wind, mini hydro, here also I have mentioned the corresponding what is the availability. So, the solar is available only during day, so it is diurnal in nature, and this wind and mini hydro are based on the geographical locations, the availability of the source. And whereas the diesel generator, which is means shown here, this is the dispatchable source of energy, whereas this all three renewable energy sources are coming under non-dispatchable source of energy. Okay. So, here I have shown the source, the corresponding control, whether it can be controlled, then it is dispatchable. If it cannot be controlled, it is non-dispatchable. Then the availability also it is mentioned, and the diesel generator, as it is it can be controlled, it is available any time or all the time, you can say. And the output of this corresponding local generating units. So, for solar PV already we know it is DC, it gives DC output. Similarly, for wind energy and micro hydro or the mini hydro, so we get it gives a AC output, and the diesel generator is also giving AC output. Okay. So, this is based on the source, availability, power output, the control, and corresponding power electronics interface. So, power electronics interface, if I will say, so if it is connected to the DC bus, so DC output connected to DC bus, then DC to DC converter, DC output connected to AC bus, we need what? Inverter. Similarly, when it is giving AC output and it is connected to DC bus, we need the control rectifier. We are connecting to the AC bus, then we need a inverter. Okay. So, sorry, here it is just opposite, just AC output. If we are connecting to DC bus, this is the control rectifier, this is AC output connected to the AC bus. So, there will be a bidirectional or two stage converter, AC to DC, again AC, and similar is the case for this mini hydro. Mini hydro and wind are almost having similar type of power electronics converters, and coming to the diesel generator, we do not need any power electronics converter. So, this is about the local power generating units. I have given one overview of it, and now in our in the theme of our topic, that is the design of mini hydro power plant and its integration with DC microgrid. So, our focus is on DC microgrid. So, obviously, we will talk about the advantages of DC microgrid, why nowadays we are moving from AC microgrid. AC microgrid is already established one, in our power system is totally AC, and because of this renewables, we are again moving towards the DC based systems from AC to. So, here I have shown a comparison between the AC microgrid and DC microgrid. So, here if you see the integration with the renewable energy sources, and when we are going for the sources like PV and fuel cell which gives a DC output. So, and I am connecting it to the DC microgrid. So, we do not need any power electronics converter, whereas if I am connecting it to a AC microgrid, we need a power electronics converter. So, this makes a, so there is a need of extra power electronics converter here, and then again if you are integrating the DC system to the ESS, means energy storage system, then we do not need the direct integration is possible, whereas for the AC microgrid direct integration is not possible. And again if you are supplying to the DC load, which are nowadays the DC loads are the LED, the BLDC fan, those are coming as a DC load, the EV, okay, then directly we can integrate to the DC microgrid, whereas we need a power electronics converter extra for AC microgrid. So, these are the means here what I want to say, it is not that AC is not totally obsolete, AC is still existing and we cannot immediately replace AC system, but we are moving from, because of the obvious, these are the advantages for which we are moving from AC system to the DC systems. So, and also the problems with the AC systems are, it gives the power quality issues are present. Yes, it is present in case of AC system. Need for synchronization required in case of AC system. Frequency you have to maintain for AC system, whereas this power quality issue is absent in case of DC system. You do not need any synchronization and there is no frequency maintenance issue. And coming to the skin effect, yes, it is present in case of AC microgrid, whereas it is absent in case of DC microgrid. And but if we will see about the demerits of the drawbacks of the DC system, the protection is well established, fully explored, or the means it is fully developed. So, it is not expensive in case of AC, whereas there is no standard till now for DC based systems. So, it is still underdeveloped, and so when we need any protection, it is still expensive, and that is the problem with the DC based system. So, for the AC systems, the standard is already, it is proper standards are available, whereas for the DC few standards are available. Okay, it is still in research state and we need to explore more on it, and as it is a AC is already established system. So, we need initial investment is low, whereas for a DC based system initial investment is high. So, though there are so many advantages, but few disadvantages, but because of all the advantages, we are again, as we are moving from the fossil based system towards the renewable energy based systems, again we are preferring trying to go from the AC to DC based microgrids. Okay. So, this is about the advantages. Then there are certain, as already I mentioned, there are no proper standards, but what are the standards available, that I have tried to mention here. So, the standards potential voltage levels for a DC microgrid is, for a low voltage level it is less than 48 or equal to 48. We are mainly actually working in this till now. We have published many papers, means with wind PV based 48 volt LVDC microgrid system. Okay. So, this can be used for this low power applications having this automobiles, USBs, okay, and small, for the small houses, and for these fans and standalone loads we can go for this less than 48 volt system, and these are very safe for the as per the safety factor, because the voltage is low. So, we do not need any extra protection for it, and in the second stage the voltage level is between 48 to 100, where again it is for the low power applications, lighting, residential and telecommunication industry, for the standalone facilities. Okay. Here still it is, as it is within 100, we do not need any extra protection. Okay. And but the load we can go up to few kilowatt, not more than that. Low voltage again, because if we will go for the high power application, again current will be very high. So, there we need again the protection. So, till 100 volt for the 48 as well as 100 volt system we do not need such proper protection, whereas when we are going beyond 100, that is 100 to 400 volt is one standard available and 400 to 1500 is the second one. So, for this is the medium voltage, you can say for this microgrid application, not, but 400 volt is still, if you will see in power system 400 volt is also low voltage system, but here I am saying with respect to DC, okay, do not take it otherwise. So, this is normally used for residential and major applications such as data centers and industries, and when I am going beyond 100 and above 120 volt, okay, which is lethal, we need proper protection for it. Okay. So, beyond 100, 20 and up to 1500 we need protections, but the power level for this up to 400 the power level is 500 kilowatt, whereas for from 400 to 1500 volt system the power level means power limitation is up to, we can go up to 10 megawatt, but with a proper protection system. The applications for 400 to 1500 volt are shipboard, aircraft transportation and traction, etc. Okay. So, where so these are the potential means in the DC microgrid and the corresponding voltage levels, the standards available. Apart from this, there are few other voltage levels also available in literature, where you can see this is 120 volt, 200 volt DC microgrid, 210. So, this is not properly standardized, but it is reported in literature, that is 360, 400 again up to 700 volt. Okay. So, that I have marked here. So, this is I am talking about the from the microgrid, AC microgrid, DC microgrid, then I have discussed about the advantages of DC microgrid. Mostly I have focused, though I talked about the disadvantages of DC microgrid, and then what are the it is not having proper standard, but what are the still what are the basic voltage levels we are operating at. Okay. So, this is about the potential voltage level of the DC microgrid. So, this is the first part of the today's lecture, that is the overview of microgrid and the classification and all. In the second part, I will talk about the energy storage system and why it is needed. What is the necessity of energy storage system when I am going for a renewable energy based microgrid. So, when because the as already mentioned, the renewable energy are intermittent and unpredictable in nature. So, and why it is unpredictable and intermittent, because it is influenced by weather or due to the this PV as due to the diurnal variation. Okay. So, this renewable energy sources is unpredictable. So, if there is diurnal means during night time, if there is no sun, so you cannot supply, you cannot shut down your power system or the whole system. So, you need something to supply to the load. So, that is why we need a storage. Okay. So, when there is no source or less amount of generation, we need a backup unit which can supply to the load, or when there is a excess generation, we also need to store it, and when there is less generation or no generation, we can supply back to the load. So, that is why that is the main role of the storage in case of the this renewable energy based system, or you can say it is in a microgrid application. So, then coming to the what are the standards means different type of storage available. There are many storages on but broadly it is divided into 4 types, that is electrochemical energy storage, fluid storage, mechanical storage, electromagnetic storage. Okay. So, here this when I am means I am not going to discuss about this all 3 storages. I will mainly focus on the electrochemical, and that too under electrochemical energy storage I am will be talking about the mostly used storage, that is the battery energy storage system, and apart from that I will talk little bit about the supercapacitor also. So, then when I am using this energy storage for microgrid, what advantage it provides? It provides it can be used as a spinning reserve and can be used for energy management, okay, to accommodate this new renewable or the if you are adding renewable energy sources to it. it gives higher efficiency as well as provides a better means economic in nature. It is cost effective and it provides better power quality and improves the reliability of the system. Okay. And also gives a better voltage and frequency regulation if you need to control the this renewable energy in a smoother way. And the last point is it gives a better asset utilization of the generation as well as the transmission. So, these are the needs for which means the energy storage is required in microgrid applications. Okay. And in now when I am talking about the microgrid and the use of energy storage system here. So, it is basically based on the whether it is for high power requirement or for electricity spectrum, storage spectrum or for high energy requirement, high energy density means high energy applications. So, you have it is divided into 3 main categories, that is best for the high power applications, it is mainly used for power management. Okay. And so, the time of the means for how long you need the storage. So, based on that means it is basically for the high power the time requirement is second or less than that, for very fraction of second you are using this, and it is for the power management application. And when there is a bridge means there is a switching between the two sources, then the storage gives a backup. At that time the duration is between second to minutes. Okay. For the electricity storage spectrum means for the bridging power application means when there is a switching from one source to the other. So, at that time this energy storage provide a backup and the time duration is between the seconds to minutes. Okay. You just see first one is for a very less time it is giving a backup, whereas the second application when there is a switching it gives a backup from between the seconds to minutes. And for the higher energy density means for the energy management applications it gives a backup for hours or in days also. Okay. So, where your applications like PV wind power and when you are going for the energy management applications. Okay. So, this is about the application of means specifically energy storage, how it is used in microgrid and for how long. Okay. So, here you have 3 options for less than second, between seconds to minutes and for some hours or some days. Okay. Then as already I have mentioned, I will talk mainly about apart from all different type of energy storage, mechanical storage, electromagnetic storage, I am focusing on the electrochemical storage, which is very old age technology. Okay. And among that you know this commonly used storage is the battery mostly used, and then now supercapacitor is also coming into picture. Okay. So, between this battery and supercapacitor, this has two features means complementary characteristics. Battery gives a low specific power, high specific energy, less life cycle and less capacity of self discharge. Okay. So, correspondingly less cost per watt hour, whereas the supercapacitor gives a less specific energy. So, that means battery is having high energy density, whereas supercapacitor is having high power density. Less specific energy, more specific power, fast charging, and but it gives a longer life. This is a less life cycle. Okay. And high self discharge rate. So, that is why means why I want to focus on this. These two type of storage which is giving a complementary characteristics can be used together. So, that means for a longer duration we can use battery means forming this if I am using battery and supercapacitor together. So, it forms a hybrid energy storage system. Okay. So, the use of supercapacitor is for a shorter duration, that is for the transient operation. So, we can improve the battery life. For steady state operation we will be using batteries, and for transient operation we can choose supercapacitor. Okay. So, that is the combination of, so nowadays battery supercapacitor combination is also giving a very better option for this microgrid applications. and we are also working on this hybrid energy storage, hybrid energy renewable sources as well as storage. So, and different type of batteries that are available here till now is lead acid, lithium ion, nickel cadmium, and the VRBs, and also sodium based batteries are also coming up, which I am not much aware also, but just standards are lead acid, lithium ion are mostly used. Okay. And I am not going about to discuss about the type of batteries or the chemical properties of it. I will talk about the sizing analysis of it, that I will cover in the next slide. Okay. So, sizing means, as we are talking about the batteries, means the energy storage, its uses and why it is important. Then when I am going for a renewable energy based microgrid, I need to design the, means take the, what should be the size of the battery, how much long it can give a backup for the system. So, for that, so there are I will take two examples. One is first for a standalone PV system, okay. Battery sizing for a standalone PV system, and battery that will be used for a DC microgrid. Okay. So, but that is both are for the standalone only, but it is for a load, and this is in the first case I will talk about the whole system, not only the battery sizing, the complete simple example, very simple example I will tell here. The each component of the standalone system will design. Okay. Then I will give one assignment on that, then I will go to the sizing of the battery for a DC microgrid application. So, these two things are left, so that I will discuss now. So, coming to the design of the complete standalone PV system. So, where each is having a component like the PV array, the charge control, means it is having the, if the standalone PV system is supplying a DC load, it is through a charge controller. Okay. And if the PV, means if there is more, the generation is more, it is we need a storage. So, which is charging and discharging depending on the load, and if you want to supply AC load in the household, you want to supply, we need a power electronics. This is a simple example. So, battery through, means the battery is supplying to the AC load through the inverter. So, the components are the power electronics converter, are the charge controller and inverter, and the you can design the system for the AC load or DC load. Okay. And here each component we need to do the sizing analysis, means decide the specification for how much load, what should be the size of the PV array, what should be the size of the battery, what should be the size of the specification of the power electronics component used here. Okay. So, let us take one example. So, before going to the example, first we will see the design steps. Okay. So, to depending on which type of system you are going to supply, if you are going for a DC supply, means you have to first calculate the load. Here I have mentioned for a AC system, means the system is completely, means having the PV array, charge controller, battery, inverter and AC load, this. Okay. So, this part I am supplying. So, I have this 5 components, and for that first you have to decide for what is the load of that household. Okay. So, you have to prepare a AC load chart, first step. Okay. And you have to correspondingly calculate the energy means how much energy is required to supply that power. You will calculate the total power requirement. Okay. That is the, by preparing the AC load chart, then calculate the corresponding energy estimation in watt hour. Okay. Load in watt and energy in watt hour. In the second step, you have to determine the size of the size and choice of the power electronics components. The power electronics components I have shown as it is supplying to the AC load. So, it is a charge controller as well as, but we have the inverter here. So, the power rating, the voltage rating, voltage and current rating of the input and output of the inverter and the charge controller will decide, that is the inverter and charge controller selection in the second stage. In the third stage, we will do the main thing, that is the determination of the size of the battery. Okay. And in the fourth stage, we will determine what is the PV module size required, so that it can supply that amount of the load. Okay. So, this is the third step is the battery sizing, and in the fourth stage we will do the solar PV sizing. So, that I will be explaining with the help of a simple problem. So, here the problem is the question is the design a PV system for a factory which contains 1 HP motor operating for 4 hours a day, 8 tube lights each of 40 watt operating 7 hours a day, 3 fans of 60 watt each running for 6 hours a day. Hello. Sorry for the interruption. There is a power failure, so we delayed by 15 minutes. So, let us start the last part of this session. So, I will complete it with a design problem. So, already let me start from the beginning again. I will read out the question. So, design a PV system for a factory which contains 1 HP motor operating for 4 hours a day, 8 tube lights each of 40 watt operating for 7 hours a day, 3 fans of 60 watt each running for 6 hours a day. Consider a 1 day autonomy of battery. So, I will come to this part later. First, in the design step, what I told, you have to prepare a AC load chart and correspondingly estimate the energy in watt hour. So, first we will make a table considering all the appliances here 1, 2, 3 we have one motor, okay, tube light and fan, corresponding power ratings are given in this. So, that is the motor is consuming means 1 HP power, that is 746 watt, the number one number, and tube light 40 consuming 80 watt, and it is 18 numbers, and per day it is running for 7 hours. Similarly, the motor is used for 4 hours a day, and the fan which we have 3 number of fans. So, and it is used for 6 hours a day. So, correspondingly from each component power appliances, we can calculate the corresponding wattage requirement. So, tube light 40 watt each, 18 numbers, so 320 watt. Similarly, fan 60 watt each, 3 numbers, so 180 watt. So, total wattage requirement or the load requirement is 1246 watt if you add up. So, that is the AC load chart we have prepared, and it is used for how many hours per day. So, the motor is used for 4 hours a day, the tube light is used 7 hours, and the fans are used for 6 hours. So, correspondingly by the power into the number of hours, the energy required per day in watt hour is calculated to be like this, just power into the corresponding number of hours. So, total energy requirement is calculated to be, means if you add up, so it gives us 6304 watt hour of energy. So, that is the we have prepared the load chart and correspondingly calculate the energy requirement for the household. Okay. So, in the second step we have to calculate or design the power electronics components which are the inverter, and the second one is the charge controller. So, first if you will see the inverter, so the total wattage requirement is, the power requirement is 1246, that is the output, and the output energy requirement is 6304 watt hour. So, if you will assume efficiency of the inverter, so this is a design problem, so we can assume it is let us take it is greater than 90. So, it can vary from, you can take as per your design 92%, 96%. So, here I have taken 93% for the inverter efficiency. So, output, and here this is the output power, and so correspondingly what will be the input, that is the output by the efficiency. We are calculating the input power requirement. So, it is in volt ampere, that is the rating of the inverter. So, inverter capacity power rating is 1340 volt ampere, and total input energy is this 6304 divided by 0.93. So, that gives the total input energy for the inverter. So, this is how we are deciding the inverter capacity. Then coming to the charge controller selection. So, we have to first assume a system voltage. So, for this problem we have taken a system voltage of 24 volt. You can do your system design also taking a example, let us take 12 volt or 48 volt system. So, here I have taken a 24 volt system. So, we are fixing the voltage by choosing the voltage of the system. So, from here we have mentioned the total watt hour energy requirement, that is the input of the inverter, and this is the wattage requirement of the inverter, and we have fixed the voltage, system voltage. So, what is the charge controller current rating? The power divided by the voltage will give you the charge controller. You can calculate, recalculate it whether I have done any mistake or not. So, you can see this is the charge controller specification, this is the energy requirement, power requirement, we have fixed, assumed the voltage. So, correspondingly we have calculated the current rating of the charge controller. Then in the our main goal is to decide the size of the battery. Okay. And in the question if you will see, I have consider 1 day autonomy. It may not be, it can be a 0 day autonomy or 1 day autonomy or 2 day autonomy, it is possible, but what is the meaning of this autonomy? First you need to understand. So, autonomy means the battery should be capable of supplying those many number of cloudy days. Okay. So, if the number of 1 day autonomy means the battery should be capable of, normally if 0 autonomy the battery should be capable of supplying for 24 hours, whereas for 1 day autonomy it should be capable of 24 plus 1 more day. So, 48 hours backup it should be able to give. Similarly, if it is 2 days of autonomy, so 48 plus 24 again. So, like that you can calculate the size of the battery. So, coming to the battery sizing, so this number of days of autonomy is a very important term you need to understand. And then coming to the depth of discharge, what do you mean by DOD of the battery? depth of discharge. It indicates how much of the total charge of the battery can be used, means we cannot discharge the battery below 50%. Okay. So, the depth of discharge of the battery, it may be given, but that is a standard. You can take when you are doing this design problem, you can assume a DOD of 50%. So, from the energy requirement, what is our we have calculated the total energy required 6780 watt hour. So, considering the 2 days means 1 day autonomy. So, it should be able to means the size of the battery should be double of that. Okay. So, 1 day autonomy. So, it should be able to supply for 48 hours. So, that is why the water in the calculating the watt hour requirement, the water it is the actual calculated energy into twice of that is due to the autonomy. And as we have fixed the voltage, again it is mentioned here 24 volt. So, what will be the ampere hour rating of the battery? So, that watt hour divided by the voltage will give you the ampere hour rating. And again as you cannot discharge the battery below 50%. So, considering the DOD of the battery 50%, the actual capacity of battery should be this 565 ampere hour divided by 0.5 will give you the actual ampere hour capacity of the battery. So, this is when you are trying to design the size of the battery for to supply the household having these many loads, and you have to make a battery sizing. So, you are not going to make your own battery, right? You have to choose from get it from the market. So, you can standard batteries are of different ampere hour rating. So, for this example I have chosen 112 volt 150 ampere hour. You can take your own battery 100 ampere hour also. So, for 12 volt 150 ampere hour battery, so you need to have the your system voltage is fixed at 24 volt. Okay. So, the number of batteries need to be connected in series is 24 by 12. So, 2 batteries you need to put in series because it is of 12 volt each, and as the capacity actual capacity of the battery is calculated to be 1130 ampere hour. So, the number of batteries need to be connected in parallel is each battery is of 150 ampere hour. So, 1130 by 150 it is nearly 8 batteries need to be connected in parallel. So, this is the sizing of the battery. So, all of you please note it down. After the end of this, if you have any doubt, I will clarify it. So, after this sizing of the battery, we will go to the next last part of the sizing, that is the PV sizing of the PV system. So, we have calculated the in the energy calculation for the supplying that amount of load, we need 6780 watt hour. Okay. And the battery considering because the PV is supplying to the charge controller and it is charging the battery, then so there is a coming of battery efficiency. So, how much energy should come from the PV module, considering the battery efficiency of here also you can assume, this is the assumption only 95% I have taken, you can take your own value 90 means greater than 92% also you can do your calculation. So, these numbers will vary. So, considering that the energy required from the PV module is calculated to be 7140 watt hour. Okay. So, for this watt hour, so to calculate the wattage requirement of the PV system, so how much means the sunshine hours, means for Indian scenario you have to take per day how many sunshine hours means sun is available. So, average it can vary between 5 to means 4 to 6 sunshine hours. So, here we have chosen a sunshine hour of 4.5 hours. So, watt hour divided by number of sunshine hour will give the PV module wattage, that is here it is calculated to be 1590, 7140 is the wattage required from the PV. Then the number of sunshine hours we have assumed it for the Indian scenario 4.5 hours, and the PV module wattage rating required is 1590 watt. Okay. So, again, so as it is a total, so to supply that many loads, okay, so we need a PV module of this much wattage, but we cannot get a single PV module of this wattage rating. So, a standard PV module, there are different standards available. here we have chosen a PV module of 150 watt 12 volt, okay, and the current rating is the PV current rating is 12.5 ampere. For this, so from this wattage rating and watt hour rating will decide the number of series and parallel connection. So the system voltage is fixed for 24 volt. So the PV module we have chosen the voltage is 12 volt. So number of series connected PV modules are 24 by 12 is 2, and to decide the current rating, the ampere hour rating again for the PV module is 565 ampere hour, okay, and that previously we have calculated, if you will see in the previous slide, and from by dividing by number of sunshine hours we are getting the total current rating. So total current rating required by the need to supplied by the PV is 125.5, and so by taking a each PV module of 12.5 ampere size, so total around 10.1, or this is giving a means as a whole taking a higher rating, we can go for a 11 number of PV modules need to be connected in parallel. And in the other way around, from the this watt hour rating also dividing by the watt single PV module watt, we are getting the similar number 11. Total watt hour rating is 1590, and if you will divide it by 150 watt of single PV module, so number of parallel connected PV modules are 11. So this is the for a simple household appliances, we are going to design a PV system, means having all its components. So here I have covered all 4 components, means the 3 components basically, the PV sizing, the battery sizing, then comes the power electronics component, under that the charge controller and inverter sizing. So now I will give you this 2 assignments to solve. I will post these questions in the group, and for here also I will circulate, so you can try it, and towards the end you have to submit these 2 assignments. Same for one for the same AC load having different ratings, and for a DC load simple questions. Okay. So try to solve it. Next is the, so this is a standalone PV system. Now for a DC microgrid, when I am going to, so here I have not talked about the, when I am interfacing with the DC bus, the battery is interfaced to the DC bus. So we need a charging discharging, and it is interfaced to the DC bus through a bidirectional converter. Okay. So this is the circuit. I am not going to talk anything about the circuit today, that a special class I will be taking on this. So here this bidirectional converter, this design also will cover, but I am not talking anything about it, its operation. I am just saying how to choose the sizing of the battery when you are fixing the when you are designing the battery for a DC microgrid. So here what is the means how you will decide? First is how much load you need to supply, and for how long duration you have to, you need a backup. Okay. So backup may need from, means vary from few hours to few number of days also. So for a here I will give you a small example. For 300 wattage of load, and you are supplying and you are fixing the DC bus voltage to 48 volt, because we are designed our whole system during the power management also, you will see the LVDC microgrid having a 48 volt LVDC microgrid. So here we have tried to design the battery for to supply 300 wattage of load, and the bus voltage is fixed to 48 volt. So here how you will choose the battery rating or battery sizing? So first is, in the first step you have to calculate the battery current, and then the ampere hour. Battery means you have to either, means you have to give the voltage, current and the ampere hour capacity. Okay. So based on the load, already I have told it is a 300 watts. So that is 0.3 kilowatt of load you are designing. Okay. And you have to assume the this DC-DC, the bidirectional converter used here, which is interface between the DC microgrid and the battery. The efficiency of this is assumed to be 96%, okay, and the battery voltage. So the bus voltage is 48 volt and battery voltage is fixed to 24 volt. Okay. So, as we are fixing the battery voltage and we will step it up or whatever the during buck operation also we can get it from 48 to 24. So, we are fixing the battery voltage to 24 volt. So, the current requirement of the battery is 12.5 ampere. Okay. So, what is the ampere hour capacity of the battery? So, ampere hour capacity of the battery will be decided by the current rating, battery current rating, into the K factor, T factor. So, what is the K factor? It is the ratio between the rated capacity and ampere that can be supplied for the required time, okay, and that will be given by the manufacturer, okay, and the T factor is the temperature correction factor for ampere hour capacity, and it can be defined as the ratio of capacity at working temperature and standard capacity. Okay. Then the T factor, then the aging factor, then design margin and the overload factor. Okay. So, aging factor is to take the aging factor into consideration means it is normally multiplied by this is the IEEE standard, it is multiplied by 1.25 times, okay, considering the aging factor. So, it is the 25% extra we are taking, and this design margin normally there is a 5% extra we are taking a cushion of to consider it 5% extra we are taking. So, we are taking a oversize of 5%. So, it is multiplied by 1 that is 1.05, and similarly it can be overloaded to again 5%. So, further it is multiplied by 1.05. Okay. So, the current we have calculated 12.5. So, this K factor how we are getting, that is I will show you in the next slide. So, K factor is given by the provided by the manufacturer, and for different number of backup hours you have to choose it from this graph. Okay. So, here we have chosen for 2 hours backup, okay, and for 2 hour backup this and with this different number of volt per cell. So, for 1.75 volt per cell and for 2 hours backup, this K factor is found to be 2.61. Okay. So, this actually this will be we will be getting from the battery manufacturer. So, from there this ampere hour capacity is the current rating into the K factor is 2.61 into the T factor, that is 25% extra, that is IEEE recommended considering the aging factor, that is 1.25 into the this design margin of 1.05 and the overload factor. So, the battery capacity is found to be 44.78 ampere hour. That means when we are going for a particular load based means household application we are doing like this, and for a this DC microgrid when we are going. So, when we are trying to put this is the 44 ampere hour 44.78 means nearly 45 ampere hour battery, but in standard whatever standards are available in the market we have 42 ampere hour, then 65 ampere hour of battery. So, that is why for this is a actual design we have used in our lab, that I have shown here. So, that it will be useful while we will be going to the lab sessions. So, this we can go for 65 ampere hour, but it is much higher means so that is why we have chosen this 42 ampere hour of battery for our system. Okay. So, with this I will conclude my today's session. So, these are some of the references and the questions I have shown for the assignment I will share in the group. If you have any question you can ask. So, any question or we can end the session here. Okay, thank you all.